Good morning, everybody. I suggest we start with the first talk of this morning session. Marc Burger will speak about the real spectrum and character varieties.
Okay, thank you very much for the invitation. And I'm going to report on the spin-off of a program we outlined in this with my collaborators, Alessandra Iozzi, Anne Parot, and Beatrice Pozzetti. And most of what I'm saying today will not be found in this publication. Okay, so what are the protagonists? Gamma is a finitely generated group. G in SLNR is a real algebraic, algebraic semi-simple, and is completely sufficient for this talk to think SLNR. Even though I will, yeah, is it not? What? Oh, okay. Ah, yeah, I wondered what this means. Ah, okay. And now it's supposed to, yeah, okay. Yeah, thinking about SLNR will be entirely sufficient. Okay, so let me introduce the character variety. Now, the homomorphisms from gamma to G acquire a topology just because they are a subset of this direct product. So it's the topology of pointwise convergence, and so does the space of reductive homomorphisms. This is a subset there are all the homomorphisms from gamma into G, such that when I consider rho as a linear representation, it is a direct sum of irreducibles. Okay, so nothing fancy. The restriction to this subset is in a sense necessary if we want the following quotient to be well behaved. So this is going to be called the character variety, even though it's a terrible misnomer. So the space of G conjugacy classes of, this is the space of G conjugacy classes of completely reducible linear representations that take values in G. And this is a topological space, which is locally compact and Hausdorff for the moment. I mean, it's much, much better, but you have to work much, much more for that locally compact Hausdorff. This is our object of study in this talk. And in fact, what I'm really after is that already in the case, yeah, what I'm really after are higher Teichmüller spaces. So here, it's in fact, most of the time, it's not the whole character variety which interests me, but it's rather interesting connected components, for example. So if gamma sub G is going to be the fundamental group of a surface of the genus G, well, then for various G's, there are connected components of the character variety consisting entirely of representations of injective representations with discrete image. So these are referred to higher Teichmüller spaces. Well, because one of the examples is Teichmüller space. So the two examples to keep in mind, maybe I'm going to do this. The two examples to keep in mind, which will follow us throughout this talk, is first, we call it TG. These are the holonomy reps of a hyperbolic structure on S. Modulo conjugation. This is Teichmüller space, I guess. Probably they don't let you in at the gates of Pisa if you don't know what hyperbolic geometry is. And the second example. So this, yeah, this I should say, yeah, this forms one connected component of this representation variety. And the second example, because there are some contrasts, is what I call it PG. These are holonomy representations of convex projective structures on SG modulo conjugation. And this is also one connected component, which I don't know to whom this goes back, but this here is Goldman and Choi, certainly the 80s of the last century. Okay, so these are two very interesting examples. And now what I'm going to talk about is more specifically this talk is about the tail of two compactifications. So let's say I have a connected component of the representation variety, and I will present some results, define and present some results about what is called the Weil chamber length compactification, and at the end talk about the real spectrum compactification and the relation between both. And this Weil chamber length compactification was also known under the name of Fursten-Barreau compactification, but we decided to name it like that because it's clear what we're talking about. So this is relatively elementary to define and has bad topological properties. And this here is, how should I say, requires a lot of technology to define and study and has good topological properties. So that's the no free lunch theorem. Okay, so let's come to Weil chamber valued length functions, which is already a nice idea there. So I have to define what is the okay. What is the Weil chamber valued length function associated to a representation from gamma into G? I mean, that essentially echoes Fursten's construction. I have to say first what is we'll need the Jordan projection. So this is linear algebra. So the Jordan projection is a map from G to the closed Weil chamber. And since I said you can think G SLN, I'll just write down what it is for SLN. G is SLNR. And so, not astonishingly, so if I have a matrix in SLNR, I obtain this gadget in the closed Weil chamber by associating to G the logarithm of the absolute values of its eigenvalues, which are complex numbers usually, and you order them from 1 to n in such a way that you end up here. Okay, so this is the largest. So this is the Jordan projection, and which occurs in the refined Jordan decomposition of G. And now, so if there are questions, you should ask questions, because, but I don't think this is so. Now, if you have a reductive representation from gamma into G, we're going to associate to it this map, which takes values in the closed Weil chain. So it's a good workout. Now, little observation here, or rather no. The best thing is to illustrate what it does in the two examples. The idea here of associating not a number to element in gamma, but a vector in this Weil chamber is that we do not, in this way, we do not privilege any Weil group invariant norm on A, because in fact, it turns out that even if you think that the Euclidean norm is the most important because it corresponds to the Riemannian metric on the symmetric space, it turns out that for purposes related to Dief-Müller theory, there are many other norms, Finsler norms on the symmetric space. At least I'm connecting a little bit with that conference. Finsler norms that are invariant that are much more important, because okay, there are, in specific situations, they are bound to be connected to geodesic currents. So okay, so the first example is not going to be anything astonishing. Okay, I can remove that, I guess.
In order to get a real number, you could take a linear form if you take a real one.
I could take a linear form on A.
Yeah.
Or I could take a norm.
But you prefer. Okay. But you mostly do taking linear forms when you take the Cartan projection, and mostly norms when you're taking the Jordan projection. We can talk about it later.
Yeah, because I'm not taking a Cartan projection in this talk. So prefer not to. Okay, let's move on. So example one. Okay, example one. I mean, it's really, you know, when you have, I mean, in the first example, A plus bar, that's just 0 infinity. And I mean, and in this case, you do get a number because this is the length of the closed geodesic associated to gamma. So I don't need, you know, that's classical hyperbolic geometry. In the second example, we In the second example, I was saying, so we have a convex projective structure, and so I have to say more precisely what this means is that there is a convex subset in projective plane that is left rho gamma g invariant, and the convex projective structure on SG is given by the quotient. And now, so in our case, the Weil chamber valued thing, yeah, maybe I'm making a nice picture here. So I have to try to, so this would be the closed Weil chamber in SL3. The Jordan projection of rho of gamma is then x1, x2, x3, which are ordered. And the interpretation of x1 minus x3, this is the translation length of rho of gamma in the Hilbert metric on the invariant convex set. So, the Hilbert metric is take 2 points, take the line through it, take the logarithm of the cross ratio of the 4 points you obtain by this. So this x1 minus x3 is the restriction to the closed Weil chamber of Weil group invariant norm that is absolutely not Euclidean at all. So this illustrates the good idea of your student Frédéric and Parot of considering Weil chamber valued length functions, and then take whatever norm is adapted to your situation. Okay, now. Okay, now, so taking a page of Thurston's playbook, we're going to, in fact, we're going to want to consider this here as an element in this space, and rather, in fact, in the projectivized space of gamma of A plus valued functions on gamma. That's the classical thing. And of course, we have to make sure that our Weil chamber valued function is not identically zero, and this requires a condition. And this condition is the following. Okay, so can I move that? Condition is the following. Fact if rho reductive is not bounded, which means the image is not contained in a compact subgroup, then this thing, this Weil chamber valued length function is not identically zero. And so we get something in this quotient here, which we call the projectivized. So that's Thurston's construction. So these are just maps with values in a vector space, and I can mod out by the multiplication by a scalar. So now, if I have now, the observation is that if C is a connected component consisting of unbounded representations, then this L of C in this big space has compact closure. This is also a relatively elementary observation that really depends on the fact that gamma is finitely generated. So, okay. So that's a priori good if we're after compactification. So let me now explain how we do the Weil chamber length compactification. So I guess it's a pity I should have put this picture over there because it's a nice picture. Okay. So, okay. So essentially, so now we concentrate on one connected component consisting of unbounded representations. And this is a trick due to Morgan and Shalen, because you see, there's very little chance in general that this map, which goes from C to this here, is injective to begin with. And then, even if it's injective, since we end up in a infinite dimensional space, so continuous maps that are injective are not necessarily a homeomorphism on their image. So Morgan and Shalen construction is a construction that exactly ignores these two problems in the following way. So if we call C hat the one-point compactification of C, so remember C is a locally compact Hausdorff space, the one-point Alexandrov compactification, I don't think I have to insist, then we are going to do the following. We're going to send C into C hat cross P by sending a class of representations to, well, here we just remember the guy, and here we put the length function. And then with this, you have achieved that the image of C is open in its closure, and the closure is compact, and that's what we call the Weil chamber length compactification. And I will need the boundary of this gadget here. And that's the boundary. Okay. So now, so it's in this formal construction, it's worth spelling out what are the length functions obtained here, because so the recipe is the following. Length functions here are obtained in the following way. There are rescaled limits of length functions of representations where the sequence is forced to go to infinity in C. That's what it really is. So in a sense, I could have defined it in that way with more words, but it would have been clearer than so. So you look at all the length functions you get here, rescale them, go to infinity in whatever way, and look what you get as a limit. So now the question for us was really puzzling for a very long time, is how do I see the difference? How can one distinguish length functions in length functions obtained No. Length functions in L of C, sorry. From the ones in the boundary. Give me one reason whatsoever why there is not a length function appearing here that's equal to a length function appearing here. So person was facing this problem already for Teichmüller space, and he solved the problem in the following way, but completely well, example one, he showed that so for Teichmüller space, if you have a length function in the boundary, which is the first boundary, then there exists a sequence such that the length of gamma n tends to 0. That's if you are in the first boundary. And that is a very good reason why, you know, the length function associated to a hyperbolic metric definitely don't have this property, right? I mean, if you're inside Teichmüller space, then the length functions are, the set is discrete and goes to infinity. So, but this here, this requires the interpretation of the length functions as intersection of measured geodesic laminations and some little dynamical argument. In the second case is the SL3R case is interesting. You can't argue like that. And let me just say what is behind it. It's a theorem we showed. So beeps is always the same people. So we showed, and it's connected to the following interesting fact. So you know, of course, that the action of the mapping class group on the first boundary is topologically transitive, for example, so dense orbits and all that. In this case here, we showed that there exists a mod G, so that's a mapping class group of a surface, invariant open subset. Can one read here? If you take the, probably not. Okay, now it's better. If you take the Weil-Chamber length boundary of the convex projective structures, there is an open, so this is open, non-empty set on which, okay. On which mod G acts properly discontinuously. Which is interesting because that means we have a new phenomenon in higher rank. So you might be puzzled why I'm saying this, because in this open set here, the length functions are length functions of actions, of proper actions of the surface group on rank 2 buildings. Proper actions. And so that's connected to this phenomenon here. All right, so now I've shown you all kind of things that go wrong. Okay, so what's the general case? So the general case is the following. I think this we can. The general case requires a little hypothesis because otherwise it's wrong. Namely, we're going to concentrate on connected components that consist of representations that are non-elementary. And so here's the definition. Rho is elementary if the closure of the image is amenable, which is sort of the theme of this conference. Now I'm going to place myself completely out of it by requiring non-elementary. So for reductive representations, for rho reductive is equivalent that rho gamma is contained in a compact extension of a split torus compact. So clearly, all the representations, the components we're interested in are consists of non-elementary representations. So let's see. Okay. Okay, so to tell you the difference between things, so the first result, in fact, uses in an essential way work of Prasad and Rapinchuk. It uses exactly the input you need beside Laurent's theorem to prove that uniform lattices are never boundedly generated. I'm saying there is an algebraic input there, which is essential in that theorem, and we're using it here to prove the following, so that if, which funnily people are ready to believe, so if rho is non-elementary, then, so if I look at the set of values it takes, so that's the Weil chamber valued length function. I record all these values. It's a countable subset in A. And I look at the Q vector space generated by it. Then this generates an infinite dimensional Q vector space. That's certainly a property. I find it cute because it gives something which is not, maybe it was not completely known for the hyperbolic length. So you take a hyperbolic metric, you look at the length spectrum. This generates an infinite dimensional Q vector space. People are ready to believe this for all kinds of dynamical reasons. But so that's one thing. And I call it proposition because what is behind is really the theorem of Prasad and Rapinchuk, which one has to exploit in a reasonable way. Now the next result will be we'll use the real spectrum compactification. So yeah, so let me put it here. Yes, okay. So the next result says several things. I need a little notation. Namely, okay, I'll just remind you what the weight lattice is. So, behind the closed Weil chamber, there is a root system. And there is what is called the weight lattice. These are the vectors in A on which every root takes integer values. And this is a this is a discrete subgroup of A, called the weight lattice. And now in the sequel, C will be a connected component consisting of non-elementary representations. Where do I have proposition 1? I mean, you can see that if I have, you see, if I have gamma, a representation that ends up in a maximal torus, and then I compose with the Jordan projection, I get a homomorphism into A. So since the group is finitely generated, this is going to generate a finite dimensional Q vector space. So therefore, this is an if and only if. This is an if and only if here. Anyway, so here is the theorem. So with this hypothesis, first, so there's a constant C depending, let's see, on A and on the connected component C, such that for any length function in the boundary of the Weil chamber compactification, the dimension over Q of the linear span of the set of values is smaller or equal to C. So suddenly at infinity, you just need finitely many values of the length function, and everything else you can compute by using linear combinations with rational coefficients. So that gives the answer. How can we distinguish length functions inside from length functions outside, right? So it's a rather drastic difference. The second thing is something which is known for the first boundary, which is a completely general fact. The set of length functions in the boundary taking values in the weight lattice is dense in the set of all boundary length functions. So when I say taking values in the, I have projectivized classes of length functions. So it means there is a representative which takes values in the weight lattice, which is, it's not reminiscent. It's exactly, in the case of the first boundary, it's exactly the integer point are dense, statements. But it has nothing to do with geodesic currents or things like that. It's a completely different source. Okay, so now I have 20 minutes for the real spectrum. That never happened. Here's a little cautionary tale. I was saying at the beginning that, so it's easy to define. So okay, so let's see. So the cautionary tale is the following. So of course the first is not a cautionary tale. I mean, we know, this is what I call the Weil chamber length boundary in the case of the Teichmüller space is the first boundary, and we know that it's homeomorphic to a sphere of dimension 6G minus 7. Now, that's the end of the good behavior. So, in fact, a very interesting thing showed by Maxime Wolf is, and I'm going to be slightly vague. No, I'm not going to be vague. I mean, he exhibited a connected component of the character variety of gamma G in PSL2R. So it's still the same surface group, the same PSL2R, but it's a different connected component. So it should have not maximal or minimal Euler number and not zero Euler, whatever. There is such a guy, such that if you look at the Weil chamber length boundary, this guy here, this connected component, okay, this is a connected component, has got some topology, and here you have Teichmüller space. So this is C, and here you have Teichmüller space, which is a different connected component. But at infinity, not only they meet, but one swallows the other in the following way. This is nowhere dense. So suddenly, for actually these very nice reasons, but okay, this component here at infinity creates so many length functions, and all the length functions coming from this component. So these are sets. No, there's not a map. There's just, I'm just in the, these are just the length functions. Yeah, sorry, yeah. Yeah, I see what I see what you mean. It's sort of, at infinity, only I'm left with length functions because I took the 1-point compactification. Understand where your confusion comes from. So this means, from the topological point of view, compactification by length functions is junk. But they're interesting. I mean, because in fact they are information coming from somewhere else. And now I'm going to describe the somewhere else. And that's the real spectrum compactification, which I will not define. I will just tell you what it does for us. So, okay. Okay, so now if you want a good topological model of this thing here, you're faced with a problem in invariant theory, because you can take finite generating set of gamma and identify all homomorphisms. No, I'm getting F is a finite generating set. So the homomorphisms from gamma into G are identified with a certain real algebraic subset of a G to the F, because you have polynomial equations, okay, being a homomorphism is. And independently of whether gamma is finitely presented or not, the Noetherian property implies that finitely many polynomials are sufficient. So okay, so it's a real algebraic subset of G to the F, and G to the F, well, that's just sitting in that vector space. And so you have to study, you have to do the invariant theory of the linear action of G given by G conjugation on this here. And this is a real geometric invariant theory. And contrary to the complex geometric invariant theory where quotients are varieties, in the real case, it's not so. But essentially, what the real GIT gives you of Richardson-Slodovi is that this is homeomorphic to a closed semi-algebraic subset of some Rn. And that just life. If you look at the reals and you look at the action of the reductive group Z mod 2Z, so that's the action of the non-trivial element, then you have an invariant polynomial that separates the orbits. But this invariant polynomial, which is called x squared, has image 0 plus infinity, right? And then you can do whatever you want. You're not going to convert 0 infinity in the real points of an algebraic variety. So that's just not. Anyways, but this is typically what the semi-algebraic set is. So for semi-algebraic, what you have to add is you're not only described by zeros of polynomials, but also by inequalities. The semi-algebraic subset is just a subset that's described by finitely many polynomial equalities and inequalities. I'm not, and these are, of course, when I said, you know, this is much better than locally compact Hausdorff. Indeed, it's much better than locally compact Hausdorff. I mean, that this is homeomorphic to a closed semi-algebraic subset of Rn says a lot about the topology. You know, for example, it implies finiteness conditions on the topology of this thing and tons of other things. So, but then it can be used to compactify. And for that, I have to so if you want so let's now pretend that we have a model, a semi-algebraic model of our character variety. Essentially, the real spectrum compactification is, very loosely speaking, are points of that thing here, but over ordered field extensions of R. So you see, this is described by polynomial equalities and inequalities with real coefficients. But I can also take some ordered field containing R and look if I have some coordinates there satisfying these polynomial equalities and inequalities. So it's kind of like with an algebraic variety base change. Here, with semi-algebraic sets, you can also make base change by being very careful. So we have to talk about ordered fields. And the ordered fields that are occurring here are ordered fields that will be non-Archimedean. That will be the sign that you're at infinity. That's the basic idea. So here, let me just give you the example of R of x. And now, so these are the rational functions. And a rational function has, so this is a rational function. And I will say that it's positive if for t large enough, R of t is strictly positive. So what happens with rational functions is, of course, there are finitely many accidents due to the zeros and the poles. But once t is large enough, it's a perfectly well-defined function, which will acquire a sign once and for all. It's not oscillating. So I say R is strictly positive if for t large, R of t is positive. This gives an order on R of x, which extends the order of the reals. And it always sounds mysterious when it says, oh, there are infinitely large elements. So here's an infinitely large element. It's x. So any real number is smaller than x. And it's completely elementary. You look at the function x minus lambda. Eventually, it will be positive. So this means this guy is an infinitely large element. Okay. The next thing you have is a natural norm on such fields. And here's the natural norm. So this ordered field comes with a norm. So P over Q, the norm of P over Q, these are polynomials, is, let's say, E is a choice. Degree of P minus degree of Q. So for this norm, X has norm E, strictly larger than 1. But if you look at any real number will have norm 1. This is basically all you have to remember let's say, are the main features of non-Archimedean ordered fields. If you have an element that has norm strictly larger than 1, it means it's really big because all the reals have norm 1. Okay, so now the theorem is that so we have a diagram of spaces where there is an open and dense injection into a compact metrizable Hausdorff space, and which I have not defined. But what is important is now the interpretation of the points in the boundary. The first, that's so this is a compactification that compactifies the objects you're interested in by similar objects. You don't go to length functions, you take limit and you have a length function, you don't know where it comes from. This compactifies representations or equivalence classes of representations with equivalence classes of representations. So points in the boundary are equivalence classes of triples. Oh, I forgot. F is a finite generating set, sorry. And E is just F to the 2, F to 2 to the N of triples rho F. Rho is a, yeah, I should have said at this point it's important that G is essentially the real points of an algebraic group, but that's what I said at the beginning without being precise. Now, this allows us to extend scalars. So these are equivalence classes of reductive representations. F satisfies is real closed. It's minimal in a certain sense. It's the smallest field in which you can conjugate this representation. So this thing here is a non-Archimedean norm on F, and some trace is a very big element. So maybe the second thing, well, I have 6 minutes to tell you what this thing is really good for. Sorry? No, here I have, I had to scratch my head to give you the description of the closed points. It's hidden here. No, with the definitions, with being more careful about the base field over which everything is defined, it's separable. Yes, but I can. This is a very private discussion because this can. So the second thing, as I promised, so you do have an equivariant surjection from the real spectrum compactification to the Weil chamber length compactification, which therefore gives you an interpretation of the length functions in terms of specific representations. Oui? Gamma lives in gamma, yeah. The speed of light introduced a finite subset. F is a finite generating set of gamma, and E is what you obtain by multiplying to the n, 2 to the n times the elements of F. What I'm saying is that there is a specific element which has big norm. Yes, exactly. N of the dimension in which this real algebraic group lives. There is a sort of out equivariant surjection, which this is essentially what leads to theorem 2 about the properties of the length functions. And I want to insist now on the following. If I have a connected component, okay, C, a connected component here. Then any semi-algebraic property satisfied by all points in C is satisfied by all points in the closure, in the compactification. This is not a statement which says, oh, if I have an inequality and I take a closure, then I have a non-strict inequality. That's not what it is. What it is, I can illustrate it in the following way. In the case of the Teichmüller space, where it's already very interesting. So I have my surface group, and I just think of its boundary abstractly as an S1 with a orientation, or if you want, a cyclic ordering. That's my surface group. There's nothing mysterious here. Then, well, every element has an attractive fixed point, gamma plus. And then I can also say, given 4 elements, I can say that they are in positive orientation if I look at their attractive fixed points, gamma 1, gamma 2, gamma 3, and gamma 4, and that they are oriented cyclically like that. So what happens now if I take any element in Teichmüller space, if I have any representation, if I have any hyperbolization, then for the rho gamma i's, I have the same picture, right? In the projective line, what will happen is that if I look at the corresponding fixed lines that correspond to an eigenvalue of absolute value larger than 1, because that's the algebraic translation of being attractive, then if these guys here are positively oriented, which is a property that only depends on gamma, then for every row, these guys will be positively oriented, right? Okay, so therefore this same thing will happen, the same thing if rho is now an element in the real spectrum compactification of the Teichmüller space in the boundary. For one thing, because F is an ordered field, I have again a cyclic ordering on P1 of F. And I will have exactly the same conformation for the fixed points, you know, corresponding, etc. Because it makes algebraic sense to talk about a line such that the eigenvalue is in absolute value bigger than 1. That's a real semi-algebraic property. And what do I have else? Well, I know that the cross ratio of these 4 points is a real number that's always strictly bigger than 1. Now this guy now depends on the representation, but it's still it's a semi-algebraic property. So therefore, the cross ratio of these 4 points here will be a number, but now in F, that is strictly larger than 1. So you might be asking where this is going. How many minutes? I have -1 minute. Okay. Now what you can do is the following. You can take the cross ratio. Let's say it's a number x. You can take its norm, and you can take the logarithm. And you obtain a truckload of cross ratios. and which you can interpret as an additive set function. So this cross ratio here, I'm going to try to see it as the value of a geodesic current on this interval cross this interval. I have lots of such products. And indeed, you can construct out of this data, you can construct a geodesic current, and you can prove that it's a measured lamination. And you see, the degeneration happens here. I mean, in that field, the cross ratio is strictly larger than 1. But when you take that norm, in ultrametric fields, where I said, you see, all the real numbers have norm 1. So if suddenly this cross ratio is a real number, it's going to be norm 1 and its logarithm is 0. That's where the degeneration happens when you're at infinity. And so in this way, you get, from a different point of view, the whole first theory about measured laminations. Okay. Okay. Thanks for your attention. Sorry for going over time.
So you define the rational points in the Weil length function compactification to be the one who have values in the root lattice. And so you say they're dense. Do you have some kind of effective density? I mean, if you take only that amount of word length element in gamma and for some distance, how fast do they equidistribute? How fast was that?
I have no idea. I would like to. I would like. Okay, so what I really would like to construct on this gadget here, for Teichmüller space is an invariant measure class, and the reason is the following. It's because if you take, to tell you the difference with the first compactification, if you take the real spectrum boundary, well, you have an action by homeomorphisms of the mapping class group on that thing. And you can, and we showed that stabilizers of points are always virtually abelian, which is absolutely not the case in the first compactification. So there is a chance that this action of the mapping class group on this compact metrizable space is topologically amenable, because, you know, I removed the first obstruction, right? I mean, stabilizers are amenable, but I would like to have a measure class on this thing here, which sort of is related to the first measure class on, but for the moment, I don't know how to do that. So,
yeah. And second question, if I may. And do you have rational points in the real spectrum compactification? What would be the
that's
analog?
exactly what I'm using. Oh, the rational points I can.
Rational points, yes. What are they?
Or we can call them integer points.
Oh yeah, integral because you're
right.
projective. Okay.
They are,
what?
Okay, they're obtained the following way. So you're in this space, that's some semi-algebraic set. And now you look at all branches of algebraic curves. And the endpoints in a specific sense create for you the fields that have representations whose coefficient field has a discrete valuation, and that's where it comes from.
Thank you.
Other questions? I have one. The fact this cross ratio is strictly bigger than 1, does this have an interpretation like a color lemma? No.
I don't know.
No.
I mean, you get the color lemma. You can get the color lemma out of considerations of cross ratios. That's absolutely true. Yes. But then it would be a specific yes. The answer is yes. In the specific case where you have the endpoints now, you have two axes crossing, and the 4 points you take are all the endpoints. So somehow that is related to the color lemma, but I wouldn't be able to reconstruct the proof right now. So,
but your point 3 is this abstract nonsense from or is this a geometry? I mean, does it
That's
follow
what
from
is
the
called-
general theory?
No, that, well, I don't know if we call abstract nonsense. I mean,
It's
this here, okay, so this here
it's a
in its
principle.
simplest application solves the Hilbert 17th problem, that every polynomial on Rn that is bigger or equal to 0 is the sum of squares of rational functions. So that's, yeah. So it's at that level, this kind of thing.
But that's purely algebraic.
No, these are called, I don't know if you call Loza-Giavezzi inequalities purely algebraic. Loja, je sais pas comment.
Lojasiewicz. Lojasiewicz.
Voilà.
Okay.
So there are inequalities.
In real algebraic geometry.
Exactly. It's exactly
the
that.
general principles of real algebraic geometry.
Yeah.
Okay. Thank you.
Okay.
No more questions. So then let's thank the speaker again.
Okay, well, it is nice to be here. And first of all, I would like to thank the organizers for the invitation. This is a joint work with Valentina Casarino. And I'm talking about the mapping properties of the spectral projections of the subLaplacian on the Heisenberg group, but I would like to give some motivation, try to explain why we are interested in to study the problem. And so I started to consider the Laplacian in the Euclidean setting. And so to get the spectral decomposition of the Laplacian, one has just, if f is a Schwartz function, one has just to take the inverse Fourier formula this is the Fourier transform, sorry, and the inverse Fourier and write it in polar coordinates, and then the inner integral, the integral among parentheses, is actually gives us the spectral components for different values of the eigenvalue of the spectral parameter, the spectral components of the input function f. I will always call these operators spectral projections, but this is an abuse of notation. Those are not even bounded on L2. That should be called generalized spectral projections. And so I will call, for instance, this number for an eigenvalue of the Laplacian, but Laplacian has a positive continuous spectrum, and so that is not a proper eigenvalue. However, when you apply the Laplacian to the inner integral in the previous formula, in the Fourier inversion formula, then since the Laplacian is acting on, sorry, I'm a kind of disaster. Is acting on the coordinate x, which appears only in the exponential factor here. And so if you move the Laplacian inside the integral, then you get a number, which is here something like negative 4 pi square r squared times the given integral. And so, as I said, you can think of the inverse Fourier formula as the composition of the function f with respect to its spectral components. And of course, the thing to do is to replace this number 4 pi square r squared with lambda, which is the spectral parameter. And so after some simple computation, you get this formula where p lambda of f, this is the operator which I will call a spectral projection, but which is not a projection actually. It is given by this formula. And so it is the integral of the Fourier transform of f evaluated at this point. Omega is a point on the sphere, and then we have the integration against this complex exponential. And this is the observation, the main observation for us, for what we want to do, is that if we take, well, here is a special value of the spectral parameter, but of course, these operators are homogeneous in lambda, and so one can estimate any p lambda to get the same estimate apart. And but if you consider this operator lambda for equal to pi, then this is an operator which is pretty much well known in harmonic analysis, and it is called the extension operator. This is the definition of the extension operator. Is the integral over the sphere, the unit sphere of a function, a continuous function, a locally integrable function g times the complex this complex exponential, and the integration is done with respect to the spherical measure, the measure on the sphere induced by the Lebesgue measure of Rd. And in well, more or less 60 years ago, Eli Stein proved that this operator is bounded from L2 of the sphere. You see, we are associating, we are mapping a function on the sphere to a function on Rd, and this operator is bounded from L2 of the sphere to Lp prime. Soon I will explain you why I write in P prime, which is the Lebesgue conjugate of the exponent p, 1 over p plus 1 over p prime is 1, is bounded from L2 to the sphere or to Lp prime of Rd if p is sufficiently close to 1. And this was a rather unexpected result at the time, but since even more famous that S, which is the extension operator, which I call S after Stein, of course, is the restriction operator R, which maps a function f, say a Schwartz function on Rd, to the restriction to the sphere of its Fourier transform. And Stein proved, and the proof was done also independently by Peter Thomas, and so they proved that the operator R is bounded from L2 of the sphere. Now we are associating to a function on Rd, a function on the sphere, is bounded from L2 of the sphere to, from Lp of Rd to L2 of the sphere, if and only if p is lesser than or equal to this number, 2 times d plus 1 over d plus 3, that we call the Stein-Thomas exponent. And otherwise, the estimate is false. This is, at least at that time, was rather unexpected. Since, you know, if you have an integrable function, an L1 function, then you can define the Fourier transform as usual by means of the integral. The definition was written, unfortunately. Yeah, okay, it is here. And you can define the Fourier transform in this way, and you get a continuous function, of course. But when you take a function in a P space with p strictly bigger than 1, then the function in infinity at infinity does not decay fast enough to guarantee that the integral converges at infinity, and so you have to define the Fourier transform in an indirect way, like as you do when you define the Fourier transform of an L2 function starting from the Plancherel identity. And you get a function which is defined only almost everywhere. So when you have an integrable function, it makes sense immediately to restrict, you can evaluate the function, the Fourier transform, which is a continuous at every single point. So you can restrict it, for instance, to a singular set, like a sphere, a set of measure 0, I mean. But if p is strictly bigger than 1, the function that you define is really defined only almost everywhere a priori, and it is surprising to have estimates of this sort, since when you have an estimate of this sort, you can define the restriction of the Fourier transform to the sphere in the L2 sense. Well, this is just functional analysis. You have to exploit the density of the Schwarz space. You have to think about these estimates as a priori estimates. You prove this estimate for the Schwarz functions, and in that case, you can, of course, consider the restriction of the Fourier transform to the sphere, because since the Fourier transform is still a Schwarz function, so in particular it is continuous. And then when you have this estimate, you can exploit the density of the Schwarz space inside LP of RD to extend the definition of R of F to the entire space, the entire LP space. And this is, apparently to look for the restriction of Fourier transform to the sphere for a function which is defined almost everywhere, it may look crazy. And in fact, it is impossible to restrict a function f, the Fourier transform of a function f that lies in L2. Since in L2, a function, the Fourier transform, the Planck-Charel theorem tells us that the Fourier transform is surjective on L2. So any L2 function is a Fourier transform. And of course, there is no hope to restrict a function which may be plus infinity or may be undefined on the sphere to the sphere. Well, there will be, of course, many other things to say about this problem, but I don't want to pursue this more. And I want only to I would like only to say that after the proof of this theorem, the Stein-Thomas theorem, Stein posed the question to determine the exact range where this estimate holds. See, you see, here I have replaced 2 by Q. And he knew that this estimate may hold also when Q is not 2. If Q is bigger than 2, it's trivial. But he also knew that in some cases there are estimates which are true, which are if Q is still smaller than 2. And there is a counterexample due to Tony Knapp, the semi-simple guy, and to Tony Knapp that showed that these estimates are false if P is too much close to 1. In fact, if P is still bigger than or equal to 2D over D plus 1, which we call the restriction exponent. And so Stein put that question. As I said, he knew, for instance, at the time that these estimates are true in the plane. In fact, he proved together with Charlie Pfefferman, which at that time was a student of him. And then after some years later, Anthony Zygmunt gave another proof of this result, and that the LQ norm over the circle of f hat, the Fourier transform is bounded by the LP norm of f in the plane if P is strictly bigger than 4/3, and Q is bigger than or equal to P prime thirds. And this is an open problem. It is a very well known among in the community of people doing harmonic analysis. It's called the restriction conjecture. For more than 15 years, nobody was able to get an estimate with Q lesser than strictly lesser than 2 in dimension when D is bigger than or equal to 3. And then it was Jean Bourgain that in the early 90s proved that there are estimates, or in R3, for instance, with Q strictly less than 2. So he improved on the Stein-Thomas theorem. This is what I mean. And it is a very active field of research, but it is too difficult for me. And so, well, I'm doing, please. Yes, well, that is a very good point. You have a good question. Well, you can here I took the sphere just because of the interpretation of the integral over the sphere, which are, by the way, these integrals are. This is the Fourier transform of a measure supported on the sphere times the density, but because these integrals have an interpretation in terms of eigenfunctions or of the Laplacian. But otherwise, for instance, you can take a subset of a paraboloid, a compact subset of a paraboloid, and the fact is the curvature. The main point I didn't want to say to discuss the restriction theory here, but the main point here to have curvature. In fact, if you have a non-vanishing Gaussian curvature, you always have a result like the Stein-Thomas theorem. So I mean, you have estimate for p lesser than or equal to the Stein-Thomas exponent. If you have a surface which is less curved, you have only some principal curvature which is non-vanishing, then the range is a bit smaller, and if you have a surface which is flat, which in the sense that it contains a piece of plane of a hyperplane, there are no estimates at all. There is only the trivial one, the estimate, the L1 L infinity estimate, which is trivial. But and so this is related to the surface, to the geometry of the surface. Yes, in fact, this is a good point. Okay, but what I want to say here is that I don't want to discuss the proof of the Stein-Thomas theorem, which is not difficult. Nowadays, we have at least 4 different proofs of that result, and at least a couple of them should be understandable by a second year undergraduate in mathematics, but of third year. Maybe here a square normale, a second year would be enough. But the key point in the proof of the theorem is that it is equivalent to prove that the restriction operator is bounded from LP over D to L2 of the sphere, or to prove that the composition of the extension operator, remember, is an operator associated to a function on the sphere, a function on RD. And so if you consider the composition of the restriction and the extension operator, you get an operator mapping a function on RD to a function on RD. And to prove that the restriction operator is bounded from LP over D to L2 of the sphere is equivalent to proving that the composition of these two operators is bounded from LP over D to LP prime over D. This is the key in the proof, since it is much more easier. You can handle much more easily a function which is in RD than a function on the sphere. And in fact, we have an explicit expression for this operator. This is a convolution operator. On the other hand, it is invariant under translation, so it must be a convolution operator, and it is the convolution with the Fourier transform of the surface on the sphere. And but my point here is that I don't know if these are the computation which I don't need, is that if you remember the formula for the projection associated to the value, the spectral value 2 pi, then this function is the same as the f composed with the Fourier transform of sigma. So this operator is the composition of the extension with the restriction operator. And so you can think of the Stein-Thomas theorem as an assertion that the operator P, here I wrote P1, I don't know why, but as I said, if the estimate hold at the point in the spectrum, they hold the same estimate, you have the same estimate every point by homogeneity, and that P1 is bounded from LP to LP prime. And this is the key to extend this theory, to do something analogous to restriction theory in other contexts. In contexts in which, for instance, you don't have a notion of Fourier transform, or in contexts like the Heisenberg group, where there is one, but it is too difficult to be handled, and one starts by studying instead the mapping properties of the spectral projections of the subLaplacian in that case. Well, I should say that this is not an original idea of us. I say us because this is a joint work collaboration, and not because I think to be, well, okay, thinking God. No, it is just because, and in fact, the first work in this direction was done by Chris Sogg in the late 80s, and who studied the spectral projections of the Laplace spectral projection of the Laplace-Beltrami operator on the sphere, and those are honest spectral projections. In that case, Laplace-Beltrami operator on a compact manifold has a pure point spectrum, and those are eigenvalues, and those are projections. And then later, together with Andreas Seeger, he extended, if you want, I can write on the board the name of these people, but you probably, well, I don't know. So the first one was Chris Sogg, and then together with Andreas Seeger, they extended the result to all compact Riemannian manifolds. So they proved something which is the perfect analog of the Stein-Thomas theorem in the context of compact Riemannian manifold. And in the case in which this would be important for us later, but in the case in which the manifold sphere has dimension 2, they have also the analogous of the theorem of Charlie Pfefferman and Eli Stein and Zygmunt. So the restriction theorem in dimension 2. I want to apply this in the case of the Heisenberg group. In the case of Heisenberg group, of course, the role of the Laplacian is played by the subLaplacian. And I'm not going to spend a lot of words about the Heisenberg group, because I for sure can assume that everybody in the audience know the Heisenberg group much better than I know. And so I want only to fix my notation. I should say that most of what I'm going to say also hold in the case of higher dimension Heisenberg groups, the groups of 2n+1 dimension. But to ease the notation, I'm only consider a 3-dimensional case. So the Heisenberg group for me is R3, equipped with the coordinate x, y, and t, which are the standard coordinates of the Heisenberg group. And then we define two vector fields, capital X, which is dx minus y halves times dt, and capital Y, which is dy plus x halves over dt. And then, of course, the commutator of x and y. Doing the commutator, we recover the derivative in the variable t, which is the variable in the center, the coordinate in the center. And so x and y generate the entire Lie algebra. And so it makes sense to consider the subLaplacian, which is a negative x squared plus y squared. The reason why I put a sign, negative sign here, is because it is more convenient to have an operator with a positive spectrum. And this is the expression in coordinates, but I'm not reading it because you know it very well. And of course, one can work out the spectral decomposition of, say, a Schwarz function on the group with respect to that operator L. So lambda is a spectral parameter, and by that I mean that if you apply the subLaplacian to these functions, p lambda of f, you get p lambda f times lambda. And so our aim here is to study the mapping properties between Lebesgue spaces of this operator. But this is also not an original idea of us, since there is Well, the first to study this mapping was Detlef Müller, more than 30 years ago, and he got a result which, in the context of the Heisenberg group, is the perfect equivalent, the perfect analog is perfectly analogous to the Stein-Thomas theorem. Now I will try to explain what his estimate, but first I would like to say, just because we are in Pisa, we are a guest of the Scuola Normale, also the university, but I would like to recall that the guy that gave to Müller the idea to study this estimate, who told him that those estimates could have been interesting, was his emeritus professor here, is Fulvio Ricci. Fulvio Ricci was visiting Stein in the late 80s, and Müller was in Princeton at that time, and Fulvio, speaking with Stein and Müller, told them, well, it will be interesting to study. Well, if you want to study this, something similar to the Stein-Thomas theorem, if you want to do restriction theory on the Heisenberg group, you should study the mapping properties of a spectral projection of the Laplacian. And the estimates of Müller are phrased in terms of non-isotropic norms. I mean norms in which the integration in T is weighted by an exponent which may be different for the exponent P, which weights the integration in X and Y, which are the coordinates on the first layer. But this was not to get a result, a more general result. It was because there are no non-trivial estimates in terms of, say, pure isotropic Lebesgue spaces. If you look for an estimate of P lambda from a Lebesgue space on the Heisenberg to another Lebesgue space, the only estimate available is a trivial one, the L infinity to L, the L1 to L infinity, sorry. And this is was proved by Müller in his paper. I should say that this is a special feature of the Heisenberg group, since if you consider, for instance, two steps nilpotent groups which higher dimensional center, then you get a much better estimate. You get estimate between isotropic Lebesgue spaces, and this depends, the feature of the Heisenberg group, since it depends on the fact that the center in the Heisenberg group has dimension 1. And the only estimate, just to say, I don't know, but the only estimate available for the Fourier transform on the line is the trivial one, the L1 to L infinity estimate. But I would say more about that when I will show you the form of the spectral projections. And so Müller proved that these operators P lambda are bounded from LP in X and Y, L1 in T, to LP prime in X and Y, L infinity in T. And this is true for all P lesser than 2. Do you have a question? Please. Sorry. Yes. No. You are why I chose this notation. No, yeah, probably it is a bad notation. Probably maybe the correct one should be to put LP here and to think of the inner integral as associated to a function, a function in X. Sorry. Yes, but the estimates are I think no, sorry, I was wrong. No, there are no estimates in the other case. Thank you. Yeah, this is a good point. And the thing that I would like to remark is that the estimates of Müller hold for every P smaller than 2. And this is an indication that in this case, these estimates are, in a sense, easier than in the Euclidean case. In the Euclidean case, you have a non-trivial interval in which around 2, in which the estimates are false. And we know that by the NAP example. And here you can go as close as you like to 2. And here that is easier. And that is point that I would like to make, since what we are doing is trying to improve on the Müller's estimates, and well, the paper of the paper of Müller is a great mathematician. His paper was published in the Annals of Mathematics. It is a nice paper. It is 30 years old, of course. So in 30 years, we learn many things, but it seems crazy to try to improve on that result. But actually, in this case, the life is easier on the Heisenberg group than in the Euclidean case. And first, I would like to clarify a point, what I mean by improving on the estimates. By that, I mean that we have to lower the exponent P prime on the left-hand side. We have to replace P prime, but an exponent which is still less than Q. Since if you replace P prime with an exponent Q bigger than P prime, then the estimate follow immediately from the estimates of Müller by complex interpolation. And so we want to get Q lesser than P. And we got to something years ago. This is a very long story, but as somebody in the audience probably know, I am very, very slow. And I'm talking of you. And so we go to which is already, if you want, a long way from infinity, because if P is very close to 1, then P prime is close to infinity. So to go from P prime to 2 is interesting. And we got this result 10 years ago, more or less. And I want only to say, in addition, that the same estimates actually also hold on the Heisenberg group, or higher dimensional Heisenberg groups. And as I said, on groups of Heisenberg type with a center of a higher dimension higher than 1, one can always get even better estimates, but I don't want to discuss that point. But well, soon after the publication of that result, we realized that notice that our estimates still hold in the almost entire interval. So for P lesser than 2, like the estimates of Müller. And later we discovered that without much effort, I mean by using something in the toolkit of everybody doing harmonic analysis, one can improve on that result and get an exponent Q which is smaller than 2. In fact, we proved in the case of H1 estimates which hold for Q strictly bigger for third, and for third, remember, is the restriction exponent in dimension 2, the exponent which appears in the theorem of Pfefferman and Stein, and at that time for P lesser than or equal to 6/5, that on the other hand is the Stein-Thomas exponent in dimension 2, since the Stein-Thomas exponent is 2 times d plus 1 over d plus 3. And in fact, we have, this is also true in the higher dimensional case on Hn, and these are the restriction exponent and the Stein-Thomas exponent in that case in dimension 2n. And this is important since I at least would like to show you that one can reduce the proof of this estimate to, if you are, for instance, on the group H1, to estimates on the plane. H1 has topological dimension 3, but one can, I hope, no, I'm not late, yeah. And at the moment, and we have a counterexample that shows that these estimates here have Q on the left-hand side, are false if Q is too smaller than this, which is the restriction exponent in dimension 2n. The restriction exponent is 2d over d plus 1. And well, but to illustrate this point, I have here a risk diagram. And since we have a conjecture, actually, and this is a risk diagram, I mean that this is a square in the horizontal coordinate is 1 over p, and the vertical one is 1 over q. And every point inside the square, the unit square, stands for an estimate from LQ to LP. Here, actual P to LQ, sorry. Here, actually, would be L1 in the center variable, LP in X and Y, and then LQ in X and Y, and L infinity in T. And this is the situation. We know that the estimates are false in the white triangle, the white upper triangle, but this follows from a Little principle, saying that if you have an operator which is invariant under translation, then the exponent on the left must be always bigger than or equal to the exponent on the right. And so, and this is easy. Our operator, I'm cheating a bit, are not exactly invariant under translation, but are invariant under sort of twisted translation. You have a modulation factor with a complex exponential also taken on. But Little principles still hold. Then the estimates are false in the two pink triangle. Well, notice that this picture is symmetric around again the second diagonal in the square, since the operator is symmetric. So it is bounded from LP to LQ if and only if it is bounded from LQ prime to LP prime. And so our counterexample showed that the estimates are false here. So for instance, if Q is too high, it's bigger than 1 over P tilde, which is the exponent, we are able to prove the estimate in the blue region, the blue hexagon, and we don't know what happens in the bow tie, inside the two gray triangles. And here things start to be harder. And here in this region, I said before that these estimates are easier in the Heisenberg case than in the Euclidean case, but here is the converse. They don't follow only from if somebody sooner or later will prove the restriction theorem, which is in Rn, I mean, which is a widely open problem, and in the sense that nobody really believes that he will be proved in less than 30 years. And it is of the same. Well, it is of the same difficulty. In fact, it is almost equivalent to the Riemann hypothesis, actually. And then that wouldn't be enough to complete the picture. But well, you know, please. Yeah, it is not bounded. Yes, it is not bounded, like in the result of Müller in this point B, which yes, it is not bounded. In fact, it is not bounded. It is bounded on this entire line in blue. Yeah. But now we have the proof, well, the complete estimate, the optimal estimate in the case of H1. This is the case, reason why I discussed mainly H1. We had been able to prove that the estimates hold for P strictly less than 4/3. Of course, we conjecture, our conjecture is that the estimate should be true also in the bow tie in the gray region, the previous picture, but we don't know in the higher dimension. In the three-dimensional case, we know that the estimates are in fact true if P still is smaller than 4/3 and Q is bigger than or equal to P prime thirds. And so in that case, we have this picture. Here I had no time to write the number, but this is, for instance, 1/4, but it doesn't matter. And now I would like, I have, yes, still 5 minutes. At least I would like at least try to explain why one can reduce the proof to in the three-dimensional case, for instance, to the plane, to study estimates in the plane, and the higher dimension to study estimates in R⁴n. And these are the spectral projections. And in fact, I avoided to write the formula to this point because it is a bit tough. And so they are given by the composition of different operators. And we have a series and then this coefficient, which of course plays a role, but and then we have here an exponential factor. Lambda k is just a notation for lambda, which is a spectral parameter divided by 2k plus 1. And the dependence on the central variable is concentrated in the two exponential factors. The second one is essentially the complex conjugate of the first one, so I won't comment about it. But and then we have this operator. I'm saying more soon about it. And then this function f lambda k, which is the Fourier transform of the given function f in the central variable. So you fix x and y, you do the integral, and you get this, which is a function on the plane. And this is the point, which depends on lambda, and you put it there, and then you have to apply capital pi, which is a spectral projection. This is also a honest spectral projection. It is bounded on L2, for instance. The square of this operator is equal to the same operator. And because these are the spectral projection of an operator, differential operator, which is called the twisted Laplacian, and which is, at least when lambda is not 0, but that is outside of the spectrum, so it's not important for us. It is an operator with a pure point spectrum. And in fact, the twisted Laplacian is a kind of a son of the subLaplacian. In fact, if you apply, it can be introduced in this way. If you apply the subLaplacian to a function f and then compute the Fourier transform in a central variable, then you get the twisted Laplacian applied. This is the definition, if you want, applied to f lambda of x and y. And you see this is the expression in dimension 2, the plane f for the twisted Laplacian, and you see that this is a close relative of the Hermite operator. Since here we have a negative Laplacian, this is the second order differential, a third part, and then the sum of the first and the last term is proportional to the square of the distance from the origin. And so the sum of these two terms is just the Hermite, essentially this Hermite operator in the plane. Here, there is also a term which is proportional to the generator of the rotations around the origin, x dy minus y dx, first order term. But if you apply delta lambda to a function which is radial, in the sense that it depends on the distance from the origin in the plane, you get the same as if you had applied the Hermite operator. And so you can trust me when I say that delta lambda has a pure point spectrum, and these are the eigenvalues like for Hermite. And okay, and so now this is again the formula for the spectral projections. And now what I want to do, I'm not reading all the computations, but what I really want to do is to estimate for when t is fixed the LQ norm in x and y of this function. Since then, we have just to take the supremum. I'm considering in t. I consider the L infinity norm in t and the Q norm in x and y, and we can use here the triangle inequality. Typically, it is a bad idea to use a triangle inequality when you have to estimate a sum, if you want an optimal estimate, since of course, the triangle inequality destroys all the interferences between the terms in the sum, but here it works. And it works, and then after some computation, you get the sum, which is bound for the norm that you want to control. And these are the operator norms from LP of the plane to LQ of the plane of pi k. Pi is the projection associated to lambda equal 1. Here we are using the fact that also twisted Laplacian is a homogeneous operator, and so one can replace pi lambda k with pi 1, and one get the series. And so to prove that the estimate, it suffices to show that this sum is bounded. Of course, the constant depends on P and Q, since for some P and Q the estimate is false. They have to depend on P and Q, and to prove this result in this range, which is the optimal one, after some having done some interpolation trick, it suffices to prove that pi k is bounded from L4/3 to itself with a norm which is almost a constant. Well, I have my first degree was in physics. You know, for physics, the logarithm is bounded. It is not a constant, but it grows very well. Not a lot. It is almost constant. And so you get, this is the sharp estimate on the other. And you get the power a quarter of the logarithm on the right-hand side. And that is enough to prove the estimate at the end point. And then you get the estimate in there. And we proved the estimate for all P and Q. We have the complete picture, but I don't want to discuss this point also since I'm late already. And well, just a comment on how the way to prove these estimates. At least I would like to say that this operator pi k are integral operators. When you integrate a function f, the input function, against a kernel which is oscillating, and it is given by the product in fact of a Laguerre function, and these are the spherical function in the representation, and so this is the product of a Gaussian times a Laguerre polynomial, and this has a lot of oscillations since the Laguerre polynomials of degree k have about k zeros, and probably exactly k zeros. And then you have also to take into account the oscillation which is due to this exponential factor, in which the role of the variables x and y and u and v is twisted. You see that here we have to multiply x times v and y times u. This is important, and in fact, it is the reason why this operator is bounded on L2, the reason why this is a projection. And it has the form, it looks like a convolution. In fact, if you bound, you take the modulus of this integral and you bound it by using the triangular inequality, you get a convolution operator, but of course, it is not enough if you want to get sharp estimates. And it is called a twisted convolution. And then, and here, start the real part, the hard part of the proof. But of course, there is no time. Moreover, you are doing geometry, not analysis. And so it will be difficult to try to explain you what happens here. But the fact is that oscillations due to the Laguerre function are concentrated in this annulus, which, however, has the defect that when k tends to infinity, tends to invade the entire space. And then, fortunately, there are very good. There are optimal estimates for the asymptotic behavior of the Laguerre function, and one exploit that properties, and then at the end of the story, at least in one regime, the Laguerre functions in the inner part of the annulus behave like a Bessel function. Outside, they behave like an Airy function, but at least in the Bessel regime, these operators have something in common, they share something with the restriction operators. Since the Laguerre function where k, where r, the distance from the origin, is not too large, just to say, I said 5 times the square root of k, looks like the Fourier transform of the the measure on the circle in this case. But this is true also in higher dimension. And then this is not the operator studied by Pfefferman and Stein. However, because we still have this twisted factor, which we cannot forget to get the epsilon, but at the end of the story, we get this estimate. And sorry, I'm late, but thank you for attending.
Late? Not at all. Are there questions? Oh.
Yeah, please.
Does the restriction conjecture in the Heisenberg group imply some form of Kakeya conjecture in the Heisenberg group?
Sorry, what did you say? I didn't. What is the conjecture?
The Kakeya conjecture? Or
you are talking about the Kakeya conjecture. Oh, great. Well, there is a Kakeya conjecture on the Heisenberg group. The case of the three-dimensional Heisenberg group is solved since many years ago. It was solved by a former student of Mattila, a girl from Bologna, Laura Venieri. And in her PhD thesis, she left mathematics. But in fact, I have never met her, Venieri, sorry. But in the Mattila gave to him the problem to find to axiomatize the restriction, the Kakeya problem, sorry, which is in a sense much, and to Cauchy stated some axioms, and then she applied her theory to different contexts, and for instance to the Heisenberg case, and she proved in fact what are called the maximal Kakeya estimate, which implied the Kakeya problem, the estimate of Kakeya. Yes, sorry, but I don't know, there is not an easy connection, a connection which at least which I know between our estimates and the Kakeya problem. But in the case of a three-dimensional Heisenberg group, it is solved, and moreover, more recently, a friend of mine who is, when I want to speak about somebody, I always forget the name, who is in Vancouver, Malavika Pramanik, together with a student of her, they got, and Joshua Zal, I think they were studying properties of random transforms, and they got a very general result from which also these estimates hold. But Malavika Pramanik is doing harmonic analysis. But Laura Venieri, yes, unfortunately, I have never met her personally. I know that now she's still in Helsinki, but she works in finance, something like that. But it is a very nice. You can find her thesis on the web, and it is very well written, and so it is very nice to read it.
Are there other questions?
Yes, please.
I mean, just to remark, everything you're looks very much like abelian harmonic analysis. I mean, at least I'm wondering, I mean, from the point of view, you first have this integration over T.
Yeah.
I mean, for P over Q and then X and Y, which from the non-abelian harmonic point of view is very natural, because you have the Stone von Neumann theorem saying that the unitary dual is you have the central character that is non-trivial. There is a unique unitary representation that's an infinite dimensional one, and then you have all the one-dimensional ones that's factored via the center. Wouldn't it make sense to rethink what you're doing in the non-abelian Fourier transform point of view?
Actually, we are also trying in the last month. I I started to work in that direction with a friend of mine, which is in Edinburgh, an American guy, which is called Jim Wright. Since on the other hand, when you compute the Fourier transform of a function on the Heisenberg group, you have a big an infinite dimensional matrix. And there is the theory which is due to, well, this is a pure harmonic analysis, but very old stuff, but to Walter Rudin, he, and also before to G.H. Hardy, of course, and they studied these estimates which are called lambda p estimates, lambda p, but for the Fourier series. Well, because for instance, if you take a series which is a lacunary series, a series in which just think of the Fourier series a function on the circle, and then if you consider a function whose spectral components are non-trivial only when n is 2 to the k, so they are very distant one from the other, because they have the different spectral component oscillates a lot, the interference also, they are almost orthogonal, just to say. And one obtains, and there are these estimated results due mainly to Walter Rudin, which are results of the 60s, of the 50s, and which can be interpreted as a spectral, as a restriction estimate in some sense. And so in the Heisenberg case, just to go to your question, you can pick up only points in the spectrum, because you have do you know you have the Heisenberg fan, which is I mean the representations yes are characterized, well, you have the Heisenberg fan, which is something like this. You have these lines which are they tend to go to the vertical line, and if you fix a lambda, one value lambda, for instance, lambda equal 1, you get then for each representation for every fixed lambda is represented by a point, and so you can you have a discrete problem, and you can take only the case which are for instance proportional to 2 to the k given by 2 to the n, and so you get I said before but you get how to say this is a word that I used before, but a lacunary series. Yes, you get a lacunary series. Thank you. And you can do the lambda p theory of Rudin, and this is to do restriction if you want, because you are restricting, you are considering only few representations, but the point is to determine of course the optimal range. So because it is possible to get good estimates also when the distance between two representation is much smaller, and we would like to understand that. But this is a very interesting problem, which has a much closer relation to with restriction theory, and so to the Kakeya problem. Oh, welcome, my pleasure. Oh, sorry.
So what is the reason you can't do it in higher dimensional Heisenberg groups? You don't know the bound in pi lambda, the analogous bound in pi lambda?
In what?
For Heisenberg groups of higher dimension.
At the higher dimension.
So,
no, we don't know the optimal estimates for pi lambda. Because,
but you conjecture they're true? So,
yes,
so it should be the same proof.
No, yes, we believe the conjecture, but actually, I believe that in that case, just a second, but I believe that in that case, do you remember? Sometimes I used the triangle inequality, and I said that usually it is a horrible idea to use it, because bad idea, because you are destroying the interference. and between the terms in the sum, and I believe that in fact in high dimensional the estimates are much more difficult, and you have to avoid to use it. And so you have to consider the entire series from the beginning. We also consider the entire series, but you have to consider also the interference between different terms in the series to prove the estimate. That is, and in fact, there is at that point, there is a much better representation for the spectral projections, which is related to the wave equation on the group. And that is probably the estimate, the representation that one has to use.
So that's a good question. So you know that pi k does not have a logarithmic bound in higher.
Sorry, with what
pi k, this operator pi k does not have the logarithmic bound on its norm.
No, it is bound. Yeah, it is bounded. It is bounded trivially at the point because because if you take the expression for pi k, which is the same in every dimension, that is just and if you take the modulus of the integral and move the modulus of the integral inside, you destroyed the effect of this number, which has modulus 1, but then you get a convolution operator, which is the convolution of the modulus of f with the modulus of phi k. But of course, modulus of phi k is a positive function. There is no more oscillation, and you get some estimate, but not the optimal one. In fact, we have a lot in the point is to get the if you want to get the optimal result, you need you cannot use the triangle inequality, in particular here. Maybe before, but here it is because you lose too much. The problem, the difficulty in doing analysis, this is the reason why sometimes I believe that analysis is even more difficult than algebraic geometry, which looks like a nonsense, but the point is that in analysis you have to do estimates. And when you do estimate, you can prove estimate, but if you lose too much, you get estimates which don't suffice to prove the result. In fact, as I said, most of the results which I quote today are unpublished because they are not a theorem. Where I said, oh, sorry. Now, what I mean is that one can prove estimate, but if they are not the optimal one,
okay. Thank you.
No one. Sorry.
Thank the speaker again. Thank you for coming back and listen to Luca Capogna, who speaks on pseudoconvex domains.
Okay, thank you very much. So again, I want to thank the organizers of the conference for their invitation and all of you for staying so late. I want to talk about some old work together with Enrico Redonne, and also some part of the work together with Alessandro Tazzi and Giovanna Citti, and Enrico, of course. This is not new work, but together with Enrico, we thought this could be a nice coda to the mini course that I gave earlier this week on Gromov hyperbolic spaces and some instances of these spaces. So I want to use a circle of ideas that are at the basis of the proof of most rigidity theorem. And in particular, together with Enrico, we provided a new proof of an old result of Charlie Pfefferman. The new approach is not a simplification of the original work of Charlie Pfefferman. It's more like a reframing. And it emphasizes that the result is doesn't have to do as much with complex analysis as originally people thought, but more with conformal geometry. So I need to repeat some of the slides. I apologize to people that I already inflicted those slides upon for the mini course. So first of all, this the definition of pseudoconvex domain in CN. We will talk about smooth bounded open sets only in this talk. If we define phi to be a sign distance function, then one can define the tangent space. This is the usual tangent space to the domain at every point. And then within this tangent space, there is a maximal complex subspace which is invariant by the complex action. So for instance, if we are on the in a hypersurface in C2, we are in R4, the hypersurface has dimension 3, the tangent space has dimension 3, and there is a subbundle, which we call H here, that is two-dimensional within this tangent space, where the action of multiplication by I is, the space is invariant by action by multiplication by I. So in the case in which we have the ball, for instance, we obtain the standard contact structure in the Heisenberg group. Okay. And in order for this distribution to be a contact distribution and bracket generating, we need some hypothesis on the domain. And the hypothesis that we're going to use is that of strict pseudoconvexity. Strict pseudoconvexity means that, again, if we have a defining function phi, we take the Levi form. The Levi form here defined, it is a Hermitian form. And if this form is positive definite, then we say that the domain is strictly pseudoconvex. This form defines also a Riemannian metric on the horizontal bundle, okay? And this is the way we are going to use it. So together with this manifold, this hypersurface, together with the horizontal distribution and the Levy form, forms a contact sub-Riemannian manifold that in general does not have a group structure. In the case of the ball, of course, it has a group structure. And we have seen instances of this also in a more general setting where instead of complex field, we can use the quaternions or the Cayley numbers in Frederick's talk earlier this week. So a domain is pseudoconvex if and only if it is a domain of holomorphic. That is, this is a natural class of domain to study holomorphic functions. Okay. It is empty in dimension 1, where every domain is a domain of holomorphic. So because this property is invariant by holomorphism, one can sort of use this kind of ideas to pose the following sort of very naive question. If there is a weak CN analog of the Riemann mapping theorem, that is every domain in CN holomorphic to the unit ball? This is true, of course, in dimension 1, but it is false in higher dimension. So examples were already known at the time of Poincaré, that he found a domain that is not holomorphic to the ball. So the question is to classify all those domains that have this property. By now, the general agreement is that there aren't that many holomorphic mappings between open set. There is some rigidity in place. And so in 74, yes. Yeah. Can you speak a little bit louder? I cannot.
Just for context, so our bounded symmetric domains are the pseudo convex, pseudo whatever.
Pseudoconvex domains,
Yeah.
yes.
I mean, bounded symmetric domains in CN are the first interesting.
Convex.
Huh?
Convex or not convex?
Yeah, they're
only the balls are strictly pseudoconvex. The
Ah.
others are not strictly.
Yeah.
Oh, because they have
Exactly.
so the flat parts in it.
Exactly.
Oh, okay.
Yes. Yeah, the word strict is that the form is definite positive. If it is semi-definite positive, they are just called pseudoconvex domain. Yeah. There is a theorem that says that if you have a strictly pseudoconvex domain, there is locally a holomorphic change of variable where the domain appears strictly convex. So that's one way of thinking of them as well. So in this classification, a big step was in 1974, a theorem of independently reached by Chern and Moser. They found differential invariance of the boundary of the domains, which can be computed. These are sort of germs, spaces of germs of functions. And so they can be used to classify, to do a biholomorphic classification of domains, assuming that if one has a biholomorphism between the domains, then this map can be extended continuously up to the boundary so that it acts on these invariants, right? And so these questions of extending a biholomorphism to a smooth diffeomorphism of the boundary was taken on immediately by Charlie Pfefferman, who proved that this is always true for strictly pseudoconvex domain. This is at this point is a 60-year-old result, the 50-year-old result. This theorem has been extended and simplified by many authors. I won't go through all the extensions. Most of these extensions are based on complex analysis techniques, SCV. And then there is one proof by Paul Young, Louis Nirenberg, and Sid Webster that is purely PDE proof of this result. The original proof of Pfefferman is really sort of differential geometry in spirit. It's based on the observation that biholomorphisms are isometries of a metric called the Bergman metric, which we introduced earlier and I will remind soon. And then he built an asymptotic expansion of the Bergman kernel that gives an asymptotic expansion of this Riemannian metric, the Bergman metric, near the boundary. And what he showed is that the geodesic flow near the boundary is basically straight. It's smoothly parameterized by the boundary, so you can use it to sort of extend mappings across geodesics that are parallel on the boundary. So in a way, the infinitesimal character of this differentiable structure given by the Bergman metric in the domain played a big role. Okay. And so the Bergman metric, it's defined through this Bergman kernel. The Bergman kernel is the kernel that yields the representation, the Ritz representation of the evaluation functional on the Bergman space, of the space of all holomorphic functions which are also in L2. So we have now a kernel B, and when we take this derivative, you see with the log inside, this defines a Hermitian metric on the domain, which is invariant by biholomorphism, because all the ingredients in the constructions are invariant by biholomorphism. So this metric, as we have seen in the mini course, agrees with the hyperbolic metric in the Ball model modulo a multiplicative constant. Okay, I already mentioned this. In our approach, our approach is influenced greatly by the work of Balog and Bonk, which I will mention in a while, and I've already talked about it in the mini course. And in particular, what we emphasize here is a set of estimates on the Finsler structure. So we don't even need the Riemannian metric, but just a Finsler structure on the metric that we want to use inside the domain. In this metric, so one thing that I want to point out is that there is this splitting of every complex vector into a horizontal part and a normal part. Now, this splitting in general makes sense on the boundary, where we do have a horizontal subspace, and we call normal subspace simply the complement of that in Cn. If we're away from the boundary but close to it, we can project every point in the domain onto the boundary, and then we use the splitting corresponding to that projection. If we are sufficiently close to a smooth boundary, this projection is unambiguously defined, and this all makes sense. So in this splitting, you can see that the horizontal directions are weighted differently than the non-horizontal direction. There is a factor square here and a factor here, but it's just a linear factor in the denominator. And so this part here looks a lot like some sort of Riemannian approximation of a Carnot-Theodori metric, in which this is a sub-Riemannian metric, and then weighted appropriately so that it blows up correctly at the boundary. And then there are these two factors that becomes closer and closer to 1 when you get closer and closer to the boundary. Okay, so this is going to play a big role. This is the only part in our proof where the complex structure enters into place. So in a series of papers, several different authors have proved that for a smooth, strictly pseudoconvex domains, even less than smooth, then this estimate holds for the Bergman kernel, for the Kobayashi kernel, and the inner Theodori kernel. So there are a lot of holomorphical invariant metrics that satisfy this kind of estimates. Then from here on, we basically forget the complex structure to some extent. Okay, so the subbundle here, H, the horizontal subbundle, is actually a contact distribution. And we are dealing with a sub-Riemannian metric. In this sub-Riemannian manifold, there is the Carnot-Theodori distance. This is the control distance associated to that bundle and to the Levy form. It's the shortest time that it takes to travel between 2 points at unit speed along horizontal lines. Okay, so again, in the case of the ball, we are dealing basically with the standard structure of the Heisenberg group, and we use the Sigan-Korani gauge. Sorry, I didn't put Sigan here. So our approach is influenced by this result from 2000 by Balog and Bonk, where they proved that if you consider a strictly pseudoconvex domain, they only need C2 regularity, endowed with either the Bergman metric or the Kobayashi metric. Then this is a Gromov hyperbolic space, and its visual boundary coincides with the topological boundary. They also show that the Carnot-Theodori metric on the boundary is determines the snowflake equivalence class of visual metrics on the boundary. And so one can apply all the theory of Gromov hyperbolic spaces in this setting And this, as we have seen before, provides some immediately some extension theorem of, for instance, of isometries into by-Lipschitz map on the boundary. So let me briefly remind, for those of you who were not at the mini course, what is a Gromov hyperbolic space. I'm recycling slides from the course. A Gromov hyperbolic space is a space that has a negative curvature at large scales. So it could be, and in fact it is, in the case of strictly pseudoconvex domain, there can be compact sets where the metric is positive. And it tells us this inequality that describes this large scale behavior tells us that geodesic triangle stay together for a while until they start to diverge. So in a Gromov hyperbolic space, there is a notion of visual boundary. So there is a notion of boundary at infinity. This, sort of is inherited also by previous analog notions in Hadamard manifold or impinged Hadamard manifolds, for instance. So you say that two sequences converging to infinity, which means that this Gromov hyperbolic product goes to infinity, are equivalent if this limit is also infinite. Think of that as geodesic rays that are at bounded distance from each other, for instance. Then we take an equivalence class. One can show that this is an equivalence relation. And we consider the visual boundaries as the quotient of all these sequences by this equivalence relation. This allows us to define a metric at infinity by taking the limit into the definition of a metric. And we get this object called visual metrics. This in general may not be visual metrics. In our settings, they actually will be metrics, but they can always be by Lipschitz to a distance function, to a true distance function. In our work, we will use epsilon equal to 1. This will give a special visual metric that happens to be a metric directly when we take the limit and has all the properties as we want. We looked at this metric already in the case of the hyperbolic complex plane in the mini course, and we saw that it gives us something that is equivalent or exactly the Sigan-Korani distance on the Heisenberg group. So two visual metrics corresponding to the same parameter, but different base points are by Lipschitz. And if we change the parameter, we get snowflake equivalent metrics, of course. So this dual relation that exists between mappings, between Gromov hyperbolic space and the visual boundary allows to encode all the property of the space inside the boundary. And in particular, we do that because this is a large scale behavior. We are not interested in the local behavior. This definition is better described in terms of quasi-isometry. So a quasi-isometry, you can see, looks like a by Lipschitz map with noise, with an additive noise that allows us not to look at what happens locally. This theorem is due to many authors, but for instance, so if we have a rough isometry between Gromov hyperbolic space, this induces a by Lipschitz map between the visual boundary. This is some sort of partial converse as well. And this is exactly the method that the theorem that Balog and Bonk used once they proved that a strictly pseudoconvex domain endowed with the Bergman metric, for instance, is Gromov hyperbolic. Then a biholomorphism between two such domains is an isometry in this metric. And so it will induce a by Lipschitz map with respect to the metric on the visual boundary. This metric will be the Carnot-Theodori metric. And so suddenly we have that this biholomorphism, without using really any complex analysis, extend to a by Lipschitz map of the two boundaries, as in the sense of their Carnot-Theodori distance. And then a lot of mathematics kicks in, like for instance, from the work of Margulis and Mostov, who proved differentiability of such mappings, and you can study properties of these mappings. So by Lipschitz is quite far away from smooth, from the result of Pfefferman, and what we wanted to do with Enrico was trying to get back to the original result of Pfefferman. And this idea of using this approach to reprove Pfefferman, I think came from Michael Cowling, and maybe from Pfefferman himself in a conversation with Michael Cowling a long time ago. So this is just a summary of all this relation between mappings from the inside to mappings from the boundary and how they extend. And again, this is the one that, maybe the more general one, and this is the one that Balong and Bonk use. So how do we measure distortion of a mapping on the boundary? We want to use the language of quasi-conformal mappings. So we define these two quantities here. This quantity is particularly maybe familiar, is sort of the pointwise Lipschitz constant. And this is the same but with the limit. And one can set, this is one of many different equivalent definition. One can set a distortion of a map to be the ratio of these two objects. And then we can say that a map is one quasi-conformal, which is a synthetic description of conformality, if this ratio is equal to 1 at every point. Okay. So if you remember, for those of you who happen to be at the mini course, we gave several equivalent definitions of quasi-conformal mappings. This is yet another one that works for one quasi-conformal mapping. So this gives us a way to capture conformality in this synthetic setup, okay? And so returning to our problem, we know from Balog and Bonk that if we have a biholomorphism between two strictly pseudoconvex domains, this extends to a bi-Lipschitz maps between the boundaries endowed with their visual metrics, or in particular with their Carnot-Carattiodori metric. And so together with Enrico, we proved that this boundary map is actually much better than by Lipschitz. It is conformal. It has one quasi-conformal. And then together with, again, Enrico, Giovanna Citti, and Alessandro Tazzi, we proved a Liouville type theorem for one quasi-conformal mappings in sub-Riemannian contact manifolds. Okay. Actually, our original aim was to prove a Liouville theorem for every sub-Riemannian manifolds, and then we just fail in doing that, and I will tell you why in a moment. Any questions so far? So let's talk about, before I get into more details, this is an instance of a sort of a dictionary that allows to translate property from bounded Euclidean domains into properties of Gromov hyperbolic spaces that came out of the work of Bonk-Heinonen and Koskela, who proved a uniformization theorem between Gromov hyperbolic spaces and essentially subdomains in Rn endowed with their quasi-hyperbolic metric. And this sort of duality is extremely rich and allows them to attack problems in a different way. And this is actually one instance of doing that. Okay. So our work is greatly influenced by the Bonk and Schramm, Balog and the paper of Bonk and Schramm. And one main ingredient that we use is the filling metric that was introduced by Bonk and Schramm. This is a way of starting from a metric space. Let's say you have a metric space, and then let's call it Z. You embed it into Z cross the interval 0, 1, and you can endow this lifted up metric space with a metric that makes this lifted space Gromov hyperbolic, and in which the visual boundary is the original metric space that you start with. So we do this with the boundary of the domain and the Carnot-Carattiodori metric. This again, because this formula uses the projection, this is well defined only into a little tubular neighborhood of our domain. But remember, in this Gromov hyperbolic setting, we don't care about what happens on compact set. So we can literally focus just on the neighborhood of the boundary. Yes, Frederick. Mm-hmm. This is a distance. Actually, this is a big point. We do have an infinitesimal version, but it's sort of a key point of the proof is try not to work with this infinitesimal version and to use only these integrated versions of the infinitesimal version. Right, that's a very good point. Okay. So we are going to use this filling metric. This is a way of extending the Carnot-Carattiodori metric into the boundary of the domain in a way that endowed with this metric, this little tubular neighborhood is Gromov hyperbolic. Okay, it provides another Gromov hyperbolic structure in the domain. So we do want to compare this Gromov hyperbolic structure coming from here, from this particular metric, to the one coming from the Bergman metric. This was already done by Balog and Bonk. So let's take two strongly pseudoconvex smooth domains and define by dk the distance function corresponding to some Finsler metric k that satisfy the estimates I just showed you above about the asymptotic behavior of the length of a vector as we get closer and closer to the boundary. And then the theorem that we proved together with Enrico is that the induced boundary map is actually one quasi-conformal with respect to the metric, to the Carnot-Theodori metric. So the key to prove this theorem is to show that so first of all, an easy step is that the induced visual metric by the Bonk-Schramm filling metric and the Carnot is one quasi-conformal to the Carnot-Theodori metric. This is because the Bonk-Schramm filling metric is built out of the Carnot-Theodori distance. So this is fully expected to happen, and it's in fact a simple computation. What is not simple is how to relate the Bergman metric together with the Bonk-Schramm filling metric. And so what we prove is that locally, if we get close enough to the boundary, so if the origin point that we use to define this visual metric is sufficiently close to the boundary, then the two metrics are 1 plus epsilon by Lipschitz equivalent. This, when you look at this theorem, it looks like this cannot be used at all, because we would like this epsilon to go to 0 in order to prove our result. But if for epsilon to go to 0, the base point out of which we send out all these geodesics has to collapse on the boundary. And then we lose track of everything, right, at that point. So this has to be used very carefully, this theorem. Now, where does this theorem comes from? This comes from this estimate between the, let's say this is the Bergman metric and the Bonk-Schramm filling metric. There is an analog theorem in the Balog-Bonk paper where they prove a version of this for every points x and y inside the domain. And instead of epsilon here, they have a constant. Now, we can refine their estimate if we move our points x and y sufficiently close to the boundary of the domain. Again, a theorem like this, if you remember from the mini course, the result of Balog and Bonk was proved by making a guess of the length minimizing curve between 2 points through curves that go up and then go down again, similar to the geodesic curves in the hyperbolic space. And so the same guess happens to work in this more refined estimates. It just takes much more care about the numbers. In Balog and Bonk approach, they can throw away a lot of constants. And here we have to keep track of every single constant in order to preserve the smallness epsilon over here. Okay. So how do we put together all these ingredients? It's through this little diagram. So let me try to explain this. At the beginning, we have a biholomorphism between a domain D1 and a domain D2. When we endow these domains with their Bergman metric dk, we know that this is an isometry. Okay, so this is the upper layer. We have an isometry between these two domains. Now, this isometry will induce an isometry between the visual boundaries endowed with the corresponding visual metrics. But you see the visual metrics here, if we start with a base point O, the corresponding visual metric that will be isometric will be a metric based at FO, right? And this point FO, we have no control. If I want to change this point, I change the visual metric by a Lipschitz transformation. And so I lose the conformality, this one quasi-conformality. So we don't want to do that immediately, right? This is sort of forbidden. So what we do is this intermediate step where we go from the metric induced by the Bergman metric, so this is the visual metric on the boundary induced by the Bergman metric, to the visual metric on the boundary induced by the Bonk-Schramm filling metric. And we proved that they are 1 plus epsilon equivalent, so assuming that O, this point here, is sufficiently close, a distance, let's say epsilon, from the boundary. Same thing on this side, because we have a good map between the two domains, this will also guarantee to some extent that FO will be closer to the boundary as well. Now, we know also that this, by construction, basically, this metric here on the Bonk-Schramm the visual metric induced by the Bohm-Schramm filling metric is conformally equivalent to the Carnot-Theodori distance. And this happens again on both sides. So you can see now that at this level, if I start from here, so now I have my sub-Riemannian structure on the boundary of the first domain, and we go back all the way over here, this composed map, even if it is built through some choice of the base point O, is independent of the point O. And so this, because we have this reference metric on the boundary, independent from the base point, we can push this this system and obtain the one quasi-conformality. But it's really sort of a lucky circumstance that we have this reference metric. Frederick? Yes. Yeah. But this is a compact set at the end, right? And this is a local problem. We are proving smoothness, right? And one quasi-conform, everything is local here. So the diagram commutes locally. Okay. Any questions about this? This is basically the main idea. Once we had this diagram with Enrico, we thought we can do it. Okay. So this yields a sort of classification result. If you want, is very naive. If we have two strictly pseudoconvex domains in C2, they are biromorphically equivalent if and only if their boundary are conformally equivalent. And this is, again, one quasi-conformal. So we use this synthetic way of defining conformality. This was known before to people in several complex variables, but this is yet another proof. Okay, and you see that to do this part, we hardly use, we don't use measures, for instance. We just use metrics to prove this part. This is a purely metric point of view. Okay, there is no measure used over here. Okay, now that we have a conformal map, we would like to prove that this map is actually smooth. And the regularity of one quasi-conformal mappings between sub-Riemannian contact manifolds follows from some sort of quantitative version of Margulis' most of differentiability that we had to prove. Then the mutual absolute continuity of Hausdorff and Pop measure. So what is the Pop measure? Pop measure is a sort of analog of the Riemannian volume element for sub-Riemannian for equiregular sub-Riemannian structures. Somehow, this is the point where the metric structure has to be compared with the measure structure that we endowed, because we have to use PDE. And we need some good mutual absolute continuity between the two. This mutual absolute continuity in general is false. Okay, but in this setting, we can use enough of it to make it work. And then we need to build a system of not harmonic coordinates, but these are Q-harmonic coordinates. An harmonic coordinate is a set of coordinates that satisfies the Laplacian equation. But here we want to satisfy a nonlinear analog of the Laplacian equation, the Q-Laplacian, that I will define soon. Then we need some sort of propagation of regularity from a map that has several components, from the horizontal layers of these components to the vertical layers. And then we need a sharp regularity result for solutions of the Q-Laplacian equation, which is kind of another story. Okay, so let me show you the sketch of the proof in the Riemannian setting, just to give you an idea. In the Riemannian setting, this proof goes back to the work of Michael Taylor, to prove the Myers-Steenrod smoothness of isometry theorem, where you use harmonic coordinates. And then Limatanian and Salo had a similar proof using p-harmonic mappings on manifolds as well. So anyway, if you want to show the smoothness of a one quasi-conformal mappings between two Riemannian manifolds, the first thing we realize is that there is a PDE involved. This is the so-called n-Laplacian PDE. And to define this PDE, we need some sort of volume, some measure. Okay, that's the first thing, because there is a divergence in there. There's some notion of energy that is to be minimized. So the measure comes into play here for the first time. Then the first step is to show that one quasi-conformal mappings are differentiable and satisfy this inequality here. This comes from one of the many equivalent definitions of conformality that we have seen during the mini course. The second step is to show that these are Lipschitz. So this is easy if there are dilations. This is an argument that I learned from a paper of Pierre Pansou, right? But in general, it can be proved also on manifold that they are Lipschitz. And then if U is n-harmonic, there is this morphism property that tells us that one quasi-conformal mappings preserve n harmonicity. So if I have a function that is solution to this PDE, then so is the composition of this function with a conformal or one quasi-conformal map. If we put together all these three ingredients, together with the existence of n harmonics, so these are coordinates for my manifold that are n harmonics. In Rn, the usual coordinates are already n harmonic. They are linear, they solve this PDE. So what we do now is we take our function, our one quasi-conformal map, we compose it with these n harmonic coordinates, and we get the components of the map. Each one of them now is also n harmonic because of the morphism property. And moreover, because it's Lipschitz, by Lipschitz, this map is also the modulus of the gradient of the map is bounded away from 0 and infinity. When you plug this bounded away from 0 to infinity in this equation, you get a divergence form equation with L infinity coefficients that by the Georgi-Nash-Moser theorem will give you regularity result. You can bootstrap this regularity result and then obtain smoothness of the solution. If we don't have this boundedness coming from the Lipschitz continuity, you can still do it using regularity theory for the P-Laplacian equation, and somehow you can bootstrap even that to some extent, okay, and still get C infinity regularity. So this is the proof, sort of a crash proof in Riemannian manifolds and in Rn. If we want to do it in the sub-Riemannian manifold, we rely on the work of a lot of people. This is just a very partial list over here, okay, that studied the analog of quasi-conformal mappings in the setting of sub-Riemannian manifold. And unfortunately, I've omitted the work of the Russian school with Vodopianov and his students and collaborators that did also a lot of work. And so there is this theory, if X and Y are Carnot groups, and F is an homeomorphism with distortion equal to 1 identically, then F is smooth and its differential is a similarity with non-zero dilation ratio at every point. So in Carnot groups, we have a result like this. The issue of finite dimensionality of this group is very nuanced, and we have seen a beautiful talk by Zhengdong Xie together for his work with Kleiner and Müller, giving us sort of the state of the art in this rigidity theorem for quasi-conformal mappings in Carnot groups in general. So beyond Carnot groups in general, we don't have dilations, right? Of course, we don't have dilation in the Riemannian settings too, but we have something else. The tangent cones are not locally by Lipschitz with the manifold. There is no sharp isomerimetric constant. This killed us when we were trying to prove Lipschitz regularity for the map, because we wanted to adopt the method of Ferrand to prove Lipschitz regularity, and we spent a couple of months on it trying to do it. We couldn't make it work even in the Heisenberg group. Tangent cones at different points are not isomorphic to each other. That's another problem. This will be Carnot groups that are not isomorphic. Hausdorff measure is not a smooth volume measure. It's absolutely continuous with respect to the volume measure, to the pop measure, but the differential, the density is not a smooth function. It has some bounded regularity. It's just enough to make everything work. And there are no harmonic or p coordinates in the general sub-Riemannian setting. Even in Carnot groups, I'm not aware of p-harmonic coordinates. There are harmonic, not even harmonic coordinates, right, in Carnot groups. And finally, there is a big challenge that comes from understanding the regularity of the P-Laplacian equation in this setting. So let me talk a little bit about PD, about the Q-Laplacian equation that plays such a big role. So in a sub-Riemannian manifold, one can define a horizontal gradient. It's the gradient of a function along a orthonormal frame in the horizontal structure. And then by minimizing the horizontal P energy or Q energy of the set, we have something called the Q Laplacian. Here, Q, in this page, Q can be any number, but in general, Q is the homogeneous dimension of the space. So the growth of the balls, right? The one that gives you the growth of the balls. This equation is degenerate because it's degenerate when the gradient vanishes and when the gradient explodes. So the ellipticity or even sub-ellipticity of this equation becomes degenerate when you go to in this point. Okay. There are some non-horizontal directions here which are not represented in the equation. One has to prove regularity for them, and the horizontal gradient may vanish. The horizontal gradient may blow up as well. Okay, so this is the definition of a Q-harmonic function. It's just the weak formulation of the equation I gave you earlier. And this property depends both on the metric and on the volume form that we have chosen. So these two, volume measure and metric, have to agree to some extent, for instance, through a Poincare inequality. And so we need to have enough regularity for this solution to make everything work. And we say that the sub-Riemannian manifold supports regularity for Q-harmonic function if Q-harmonic functions are C1 alpha, at least their horizontal derivative are held, they're continuous. And then there is this sort of weak formulation, weak differentiability that is a building step towards this C1 alpha regularity. Okay, so we are sort of axiomatizing this regularity theory. And we prove a theorem that says that if M and N are sub-Riemannian manifolds, just general equiregular sub-Riemannian manifolds in every dimension, and if they support such a C1 alpha regularity, then every one quasi-conformal map is moot. So this is sort of the first step of the Liouville theorem in every sub-Riemannian manifold. But then the issue, of course, is to find manifolds that support the C1 alpha regularity theory. And we proved that sub-Riemannian contact manifolds support this C1 alpha regularity theory. And so we can apply it to prove the Pfefferman, the analog of Pfefferman theorem. So just I take a couple of minutes to go a little bit over this regularity theory. The regularity of the p-Laplacian is a hard problem. In the Euclidean case, this was settled finally after some work, earlier work for p bigger than 2 by Uraltseva and Uhlenbeck. This was settled independently by Di Benedetto, Lewis, Tolksdorf, and then there were other proofs by Evans and other people. Manfredi, for instance, Juan Manfredi. Before our work, the only case where this was known, regularity was known, was a relatively recent paper by Zhao Zong in Helsinki, who managed to prove it in the Heisenberg group and in general in step 2 groups. Okay. Since then, Ciatti together with Giovanna Citti and Marc, they were able to extend this result to every family of Hörmander vector fields of step 2 that generates everything up to step 2. And of course, our result here was prior to Citti and Marc, was an intermediate result where we were looking at contact sub-Riemannian structures. There is only, as far as I know, one case where this is known in step 3 groups by Domokos and Manfredi, and it's a particular class of step 3 groups where the commutators are such that their techniques work. So this regularity has a very long history, goes back to, I don't know, in earlier work of by Coulon, Salov-Kost, Varopoulos, and then Balog came in as well, works of Domokos, Danieli, Graf. This is in alphabetical order, but a lot of work was done by, in the work of Manfredi, Mingione, and Zong, for instance, and then Manfredi, Mingione, Zong, and Zadowska, Goldstein. So we use this, this regularity also to build p-harmonic coordinates. And our construction of p-harmonic coordinates, this is what we mean by p-harmonic coordinates. These are coordinates that satisfy the Q-Laplacian, essentially. Okay, I don't want to talk too much about this coordinate, but it's another thing for which we need enough regularity. And we prove this result. This is sort of the quantitative version of our result, where we can show that the one quasi-conformal mappings are regular. Everything boils down to a regularity result for this kind of equations, quasi-linear subelliptic equation in the Heisenberg group satisfying this growth condition. We proved this theorem. This was an hypothesis, now becomes a theorem in this setting. And this result is due to Zong if the coefficients AI do not depend on X. But in general, for our case, we need to account for any Levy form. So we don't have a fixed left invariant metric. We have something else in the Heisenberg group. And so we need to have, we have a non-invariant, non-left invariant metric. So we need to extend that result. And this theorem, in the case in which the gradient of U is bounded away from 0 and infinity, which is the case you need in Carnot groups, because we have the Lipschitz regularity proved by Pierre Pensou, It was already proved in my PhD thesis in 1996. My original PhD thesis problem was to prove the regularity for this equation for every family of Riemann vector fields. It's still open after 30 years. And so I will stop here. I don't want to go too much into detail about this. I just want to say, at the basis of this regularity theorem, there is these estimates that were mentioned already earlier in the conference that will give you, I think they were called horizontal to vertical, or vertical to horizontal inequality. These are estimates on fractional derivatives along the vertical direction of the group in terms of full derivatives along horizontal direction. This can be, in Ormander's original paper from the 60s, this came out of the Baker-Campbell-Hausdorff formula. In Carnot group, this can be refined to great level by doing some sort of iteration among all the layers. And this has been done now by now in many different papers. We use similar kind of idea here. And also one thing that we use very strongly in our paper is this concept of Riemannian approximation of a sub-Riemannian structure. This is sort of crucial because in order to prove regularity of solutions, of the gradient of solutions of PD, what one needs to do is differentiate the equation along some direction. When you differentiate the equation, obviously in the sub-Riemannian cases, commutators will appear. And a priori, there is no regularity on the commutator. So how do we do this? Either we use fractional difference quotients, and this becomes extremely messy for the p-Laplacian, or we approximate our equation with Riemannian approximants for which the theory is well known. And then we have smooth solutions, and we can sort of use a priori methods to do to work this out. So the problem with this approach is that as you do this sub-Riemannian approximation, we all know that the curvature explodes in this sub-Riemannian matrix, and curvature terms enter into this equation, right? However, the key is to make every estimate that you make depending only on the doubling and the Poincaré inequality. And then together with Giovanna Citti, we proved that these two inequalities are stable under particular kinds of Riemannian approximation for every family of Ormander vector fields. This gives a lot of freedom in PDE to approximate this kind of solutions with smooth solutions and then work out the PDE techniques that may work. Okay, I will stop here. Thank you very much.
Yes. Are there questions?
It's lunchtime.
Not just concerning the what is it called? The Pfefferman result. So if you have just pseudoconvex domains, whatever that means,
yeah,
and the holomorphic map between them, can you expect something?
I mean, with some other condition, people have extended Pfefferman result with regularity up to the boundary of some sort, but without no condition at all, they cannot be extended. I don't think that for just pseudoconvex domain, there is a theory of extension without further, but I may be wrong, but I don't think that
maybe it could be extended to partially, I mean,
partial regularity. You remember I mentioned during the mini, I don't know if you remember, but there is some condition called finite type, D'Angelo type. And those conditions give regularity up to the boundary, and they're weaker than strict pseudoconvexity. So we are talking of 40 years of more than 40 years of work on this kind of problems. There are all sorts of variation of regularity theory. I actually don't know the sharpest.
No, I just wondered, does one know what the Shilov boundary looks like for these domains in general?
I've seen papers about this, but I don't know. Yeah,
because that seems to be the part where it should extend somehow. I don't know.
Yeah.
So the next speaker is Moon Duchin, and she will be talking about discrete versus continuous in the Heisenberg group. Thank you.
Okay, hi everyone. Sorry I cannot be with you in person, but I want to talk to you about an overview of some work that uses the kind of bridge between discrete and continuous to exploit CC geometry, sub-Finsler CC geometry, and try to answer some questions of like long-standing interest in geometric group theory. So that's the theme. And over the years, I've talked to many of you about some of the ideas and results in this direction. And in this talk, I try to kind of pull it together and think about how it all fits. Okay, so what I'll do in the first part of the talk is recall what CC geodesics look like in the sub-Finsler world. And then, as I said, try to exploit that. Okay, so what are we talking about here with sub-Finsler? So we have the Heisenberg group, we have these horizontal planes. We have a plane field in the Heisenberg group, which is the horizontal subbundle. And the theme here is that if you put any norm at all on the horizontal planes, then for admissible curves whose tangents lie in the bundle, you get a length because you integrate the norms over the curves. So if I just give you a notion of length and area in a norm, then that describes paths in this metric space. So let's take a look at how. So one thing to note is that choice of norm might be sub-Riemannian if you choose L2 on the plane. And otherwise, you're doing something sub-Finsler. So I'm going to use actually 2 or 3 main examples just to guide through the rest of the talk. And one is if I put the L1 ball on the horizontal planes, and the other is if I put a ball I called hex here because its unit ball is a hexagon. I can do this. I can do any centrally symmetric convex body to define the norm. And I'll be especially interested in polygons. Actually, a third example, but one that I haven't stuck on this slide, is I'll think about what would happen if you were able to move like a chess knight. And so the convex hull of the generating set is an octagon. That's a third example I'll bring up throughout the talk. Okay, so let's go through a description of what the CC geodesics look like in this norm. So the first observation is that if you have a path and you want to compute its length, you can just project it to the plane, the horizontal plane, take its length in that norm, and that's the length of the lifted path. This is just something that one checks. Okay, so in particular, one way to be a geodesic curve in this, CC sub-Finsler world is if your shadow is a geodesic in the norm. So for instance, if your norm is L1 and your shadow in the plane looks like this, then you're geodesic because that's an L1 geodesic. If you're hex and your shadow looks like this, you're geodesic because that's a hex geodesic. And I'll explain how concretely in a moment what the geodesics look like. Okay, but so this is a special case of this general observation that if you want to be a geodesic segment in any metric space, then you want to be as short as possible while connecting your endpoints. So what does that mean in this special case? It means that if you want to connect 0, 0, 0 and ABC, and here I'm working in, say, exponential coordinates. What I need is that if my curve is called gamma, I need that its shadow, gamma 1, gamma 2, where I forget the third coordinate, is the shortest according to the specified norm that connects 0, 0 to AB while enclosing area C, right? So that condition, which again reduces to just some basic facts about norms that you can check. All you needed was length and area. That basic condition is the condition is an if and only if condition for geodesicity. And so what that means is that there's a second type of geodesic, and to figure it out, you need to know not only the norm ball, but you need to know this other shape, which is the unique isoparametrically optimal shape. For L1, that's an L infinity shape, and for hex, it's hex. Hex is self-dual. Boozman studied these in the 1930s, and he called the norm ball an indicatrix, and its isoparametrically optimal kind of dual shape an isoparametrix. So let's stick with Boozman's terminology. So for this indicatrix, you get this isoparametrix. In general, Boozman showed that for polygons, the way to do this is to take first pass to the polar dual and then rotate by a right angle. And that might sound like a strange operation, but that's a special case of what's called a Wolf shape in convex geometry. So it has a whole nice story if you're interested in that. Okay, but so for us, what this means is that this curve that I've drawn here is an example of a geodesic in the L1 norm, the L1 sub-Finsler CC metric on the Heisenberg group. And for hex, here's an example. Okay, so just to say why, those paths are as short as possible while enclosing a certain area between their endpoints, because they follow along this isoparametrically optimal shape, right? So that's what it is to be short while enclosing a certain amount of area. Okay, so so the first type, this norm geodesic type, is in particular, you can build them by following the edge directions of that isoparametrics. So for L1, you can go horizontally and vertically as much as you want, and you'll be norm geodesic as long as you don't backtrack. And likewise for the hex. Okay, so in general, this is a complete description of CC geodesics. They're either this straight type where they project down to a norm geodesic, or they're area type where they follow along the shape of one of these isoparametric polygons. Okay. I don't know how well questions will work, but this is where I would like to ask if anybody has questions. Okay. So how does this compare to the L2 case? Well, in L2, as we know, the indicatrix is a circle, and that's self-dual. So the isoparametrics is also a circle. And that means that we can think about that straight type and area type in this case. The straight type will be, well, L2 geodesics are just straight lines. Those don't enclose any area. So you just get straight horizontal lines as lifts of norm geodesics in the L2 case. The other type is more varied. You have to take the lifts of circular shadows, and so you get these sort of familiar to everybody here, I'm sure, spiraling shapes with circular shadows. And here's a picture that I probably lifted from Enrico at some point of what the endpoints of unit geodesics look like. So this is a picture of the L2 sub-Riemannian unit sphere. And how does that compare? Right, so here's the geodesic and here's the unit sphere. How does that compare to the polygonal norms? So the thing is that you get different combinatorial types within that area grabbing geodesic world. So here for L1, I have to follow around the sides of a square, but I can do that in these 8 combinatorially distinct ways. And when I lift those, I get paths that project down to parts of squares. And the ball looks like this. This picture is definitely lifted from a paper of Emmanuel Boyard, where he was studying the shapes of balls in nilpotent and some solvable groups. Okay, so same kind of story. We have what geodesics look like, their types, and then if you plot the area over those types, you get a kind of unit sphere that has, as we'll see, as I'll describe a little bit further, flat walls and a curved roof. And so the curved roof is because we're plotting area, the height is area, enclosed area, balayage area. So we're plotting an area over these polygons. And so we're getting something that's sort of piecewise quadratic over a collection of polygons. Okay. So that was the L1 case is this first one, and here's the hex case. And so it splits into more combinatorial types. All of them have to follow around the sides of a hex shape, but depending on which side you start on and which side you end on, you have these different regions. And now there are 24 types of area grabbing curves. And when you plot the areas over that, you get a shape that looks like this. Okay, so what we're looking at here is the CC unit sphere, excuse me, in this hex metric. It's a collection of quadratics plotted over these regions that describe the ways that you can trace around the sides of a hexagon. Okay, so the flat vertical walls, where do those come? So those are cut away here so you can sort of see inside the figure. Where do those come from? Those come from the length type, the norm type. So why? Because unlike the L2 case, where a straight line encloses no area. Here, the lifts of these norm geodesics, because they can zigzag, they can enclose some area, both positive and negative. And so think for instance about the L1 case, where we know that norm type geodesics are allowed to travel horizontally and vertically. So between a given two endpoints, they can enclose a certain amount of positive area, a certain amount of negative area, or they can zigzag and enclose zero signed area. So you get this kind of range of enclosed areas, and that gives you these vertical panels over the edges of this like footprint hexagon. Okay, hopefully this is clear enough. So you get these kinds of curious looking norm balls. Okay, so why do we care? We care because of a theorem of Ponceau's, which I think is from his thesis, saying that basically these are the relevant norms, these are the relevant CC structures, these are relevant metric structures, if we want to understand word metrics. Okay, so let's use the Z2 case to kind of warm up before we pass back to Heisenberg. So in Z2, what would happen if you took a word metric and you took its asymptotic cone? So you zoomed out and you studied the structure from far away. So a simple example would be if you took the standard generators on Z2, so 0, 1, and 1, 0. The convex hull of those is a diamond or an L1 unit sphere or unit ball. And sure enough, if you think about the metric, the word metric, how do you get from 0, 0 to AB? Well, it takes A plus B length. And so if you rescale this, it becomes a metric on the plane, of course, but it becomes not the Euclidean, but rather the L1 metric on the plane. Okay, and the same thing happens if you were to take 1, 0, 0, 1, and 1, 1 as your generators. Now the convex hull is this hex shape that I've been pulling through the talk. And the large scale structure of the word metric norm, right, by which I mean count the smallest number of generators that you need to reach a point, is actually the norm induced by that shape. Okay, so in particular, what we see in Z2, and here it's fairly elementary to prove that the spelling length of a word divided by its length in the norm associated to this convex hull, the ratio goes to 1. In fact, something stronger is true in Z2, which is that there's actually a bounded difference between the spelling length and the norm length. But in particular, the ratio goes to 1 as words get big. Okay, so Ponceau's thesis is more general than just the Heisenberg group, but in particular for the Heisenberg group, it says that asymptotic cones of word metrics are polygonal CC metrics by proving this kind of ratio goes to 1 in the same way. Okay, so actually, before I put that picture up, let me just sort of say that again. So if you take the word metric length of a word in the discrete Heisenberg group, and you compare it to the length of the shortest CC path that reaches that point from the origin, the ratio of that like CC norm length and the spelling length goes to 1. Okay, so what does this mean? This means that over here, I'm showing pictures from various papers of Riemannian and sub-Riemannian geometry. And that's not what we need if we want to understand word metrics. Ponceau tells us that we need these if we want to understand word metrics. Okay, so these polygonal norms are the ones that we need to understand to do geometric group theory in the Heisenberg. Okay, so what does that tell us? That funny shape that we plotted as the unit sphere in the sub-Finsler CC metric is pretty close to, and this is an actual printout of the sphere of radius. Looks like I did what, 10? So the sphere of a certain radius in the discrete group starts to look like a rescaled copy of this hex CC norm sphere. Okay. So that's nice and extraordinarily useful, but it doesn't imply that you have some sort of geodesic tracking. So that's something that I'm going to use as a tool. I'm going to investigate whether CC geodesics are good approximation of word metric geodesics. right? So what I'm saying is I've got two different metrics. Asymptotically, they give the same length. But that doesn't mean that the sort of way of traveling efficiently in the Cayley graph is geometrically close to one of these CC geodesics that I described earlier. Okay, and I'm going to also try to take that distinction between the kind of two types of geodesics and see if it carries over to the discrete group. All right, so what are we seeing about kind of this Gromov-ian theme of CC spaces from within? We could ask ourselves, what are the qualitative features of a Carnot-Cartey-Dori metric here on the Heisenberg group, and how would we know we are in one? And we know many things about this. There's a family of dilations, there are non-unique geodesics, a lot of geodesics end and can't be prolonged, and so on. And I kind of want to be asking the same questions specific to polygonal CC metrics, because again, those are the ones that are going to help us do some kind of theory of finitely generated groups. The theme that I'm going to develop is in part that you can take the distinction between the two types of geodesics and push it forward into the discrete group and learn things about it. So I'll try to build up the theory where you can also understand words in the discrete group as being the kind of wall type or the roof type. And those are in rational proportion, and we're going to end up with many kind of P over Q laws where a certain behavior occurs like P over Q of the time. Okay, so that's where we're going. Next up, I'll kind of take all this and explain how to use it to understand group growth. But any questions at this point? Okay, hard to tell if I'm going too fast or too slow.
No questions so far.
Okay, great, thank you. All right, so let's look at a very classical question from GGT, from geometric group theory, which is growth. Let's try to understand growth in the Heisenberg group. Okay, so we'll go back to those same motivating examples I've been talking about. Z2, the integers, with standard generators, or various non-standard generating sets like hex generators or chess knight generators. So here the chess knight generators are moving like a chess knight moves on a chessboard, plus or minus 2, plus or minus 1, or plus or minus 1, plus or minus 2. So a fundamental question studied, I don't know, for maybe 100 years or so in geometric group theory is, what can you say about if you have a generating set and then you have a certain budget of generators, you have up to n letters from the generating set, which elements of the group can you reach with up to n letters? So on the left here is the picture for the standard generators. I can move in a rectilinear pattern. And on the right is some moves with chess knight generators that connect the lattice points. And so these, you know, of course, different generating sets are going to give a different answer to the question of growth. And so we'll write this down with a sequence beta n that counts the size of the ball, or a sequence sigma n that counts the size of the sphere. That's going to be the tools we use to answer this question. Okay, so these are called growth functions. What I want to do for the next couple minutes is relate group growth to lattice point counting, because I throughout this talk, I want to exploit this kind of dictionary that goes back and forth between discrete and continuous. And one of the nice tools available to me once I've passed to a polygon is it's not so hard to count lattice points in polygons. There's a well-developed theory for counting lattice points in polygons. So it would be nice if I can relate the difficult question of group growth to the, you know, possibly easier question of lattice point counting. Okay, and this picture kind of illustrates how that goes. So on the left was sort of a part of the Cayley graph for the chess knight generators. And on the right is just showing you the lattice points in Z squared colored by their size in the word metric for chess knight generators. So yellow is length 1, green is length 2, blue is length 3, and so on. And so you can see that it makes a complicated pattern, and it's going to keep making that complicated pattern. But still, it will be the case that the ball of a certain size is approximately counted by the lattice points inside the appropriate octagon. Okay, so why does that work? Why is it that the lattice point count approximates the growth? Well, in brief, it's because when you rescale, something nice happens geometrically. If you look at the spheres of small radius in this chestnut metric, they look kind of messy. Right, and by the way, just to be clear, what's going on here is that, as everybody knows, chess knights can reach every square on a chessboard, but they sometimes have to take a few corrective hops. Like to get from 0, 0 to 1, 1, you have to make a few jumps. And so at first, this looks pretty inefficient. It looks like the places you can get with length 3, say, are both near the boundary of the octagon, but also inside it. But as you start to pass to larger and larger lengths, that inefficiency gets relatively small, gets negligible. And so if you rescale a large sphere in this chestnut metric, it starts to look like a skinnier and skinnier annular band around the octagon. And that's basically why the counting works, because to enumerate the ball, it suffices to look at sort of all these concentric octagons. Okay, so in group theory, there's a super long tradition of thinking about growth functions, and a very useful tool for doing that is sometimes to use the associated growth series, which is the generating function that takes the growth function numbers as coefficients, right? And here's a table from a paper I had in the notices, I don't know, some number of years ago, about kind of these counting ideas, that shows for various generating sets here on the free abelian groups and also on the free group, what is the formula of the counting function, the growth function for balls, the growth function for spheres? What does the series look like? And then some ancillary facts about that. I put it up to point out a few things. One of them is that these counting formulas, so these are called Ehrhart polynomials, the number of lattice points inside a certain shape. Actually, they agree with the ball, the growth function to first order. And then something interesting happens sort of at the lower orders, but this is sort of elaborating a little bit on the connection between the counting and the growth. But the other nice thing to see here is the recursions. So notice, if you will, that in fact, all of these growth functions are actually not just polynomial rate of growth, but they're actually polynomials. And so they satisfy a nice recursion, a kind of Fibonacci style recursion. And the observation here is that having your growth series be a rational function, polynomial over polynomial, is equivalent to satisfying a recursion of this kind. Okay, so I'll just take a minute and I'm using this slide to motivate the question, what can we say about growth in nilpotent groups? And in particular, what can we say about growth in the Heisenberg group? Is it as nice as these? So these free abelian groups and free groups have this especially nice rationality property that means that in particular, you have this kind of recursion in the growth. Do we have any hope of seeing this in Heisenberg? I'm trying to motivate that question. And I'm trying to presage the question, can we relate it to counting in shapes, right? So here's just a quote I really enjoy from an old paper of Jim Cannon's from 1984, which I call like being Zen about groups. So this quote from Cannon is just a riff on like, who cares about rationality? And what he's basically saying is that sometimes groups have a global combinatorial structure that's particularly simple, admitting descriptions by linear recurrence. And he's saying this seems to him to be a promising generalization of small cancellation theory, which I think is an intriguing idea. But he goes on to say, the result also indicates that these kinds of groups, here he's talking about hyperbolic groups, can be understood globally. You can like picture them in your mind's eye, Cannon is trying to say, in the same sense that you can understand the integers. You have the feeling on the integers that you understand how to go from n to n plus 1. And if you just do that forever, you get all the integers. And he's saying that you should extend, that feeling should carry over anytime you have this rational growth property. You can take your local picture of a group and extend it recursively and kind of, you know, everything about the group from a finite window of data. And that's kind of Cannon's philosophical take on why we should like rationality. Okay, so just to recall, in group theory, many growth theorems, all the sort of major greatest hits theorems are about rates of growth. Rationality is not about rates, it's about a kind of regularity of growth. But let's just recall very briefly how the growth rate type theorems work. You put down an equivalence relation, a sort of standard equivalence relation to handle the change of generators. And then you say that the rate of growth becomes a quasi-isometry invariant once you've handled that appropriately. And so for the nilpotent case, we have these theorems of Bass and Givarsh from the 70s that actually work out that nilpotent groups have, you can sort of, in terms of the lower central series, you can actually write down the degree of polynomial growth, of course. And then obviously Gromov's important theorem from the 80s gives the converse and goes the other way. A group with a polynomial bound on growth is virtually nilpotent. So this is super classic stuff, but it just has to do with rate of growth. And so I'm just pointing out that rationality is kind of orthogonal. It's a different thing. It's not about, you can have fast growing rational, fast growing not rational, slow growing rational, slow growing not rational, right? Okay, so what's known about rationality? Many groups are known to have rational growth for particular generating sets, like Coxeter groups, which is an exercise in Bourbaki. The work of Cannon that he was riffing on in that paper, plus work of Thurston, plus work of Gromov, tells us that hyperbolic groups, we sort of know enough about their geometry to declare that they have rational growth in any generators. And in particular, this really does come from a control of the geometry of their geodesics. Like that's how these kinds of things are proved about hyperbolic groups. So then there's this kind of counterpart theorem. There's a paper of Max Benson's from the 80s where he shows the same thing for virtually a billion groups. He doesn't think about it geometrically, he thinks about it very algebraically, but you can rephrase his proof geometrically by saying, we understand a lot about the shapes of geodesics in virtually a billion groups. And so we can do the same thing. We can show rational growth in any generators. Okay, so note how much you kind of have to know about the geometry to be able to do something like, from my point of view about the geometry, to be able to do something like this. You're not just thinking about specific generators, but you kind of know enough structurally to talk about any generators. And rationality can be destroyed by change of generators. Unlike the growth rate, rationality really can be destroyed, if you, as we'll see, if you change generators. It's natural to be curious about the Heisenberg group. It kind of, sort of, in some sense, the closest miss to an abelian group. And in the 80s, the same Benson plus Mike Shapiro independently showed that in standard generators, Heisenberg does have rational. I'll write down the actual growth function on a slide to come. But there's this fantastic work by Michael Stoll in the 90s that shows what I said a moment ago, which is that it can depend on generators. So in particular, the higher Heisenberg group, H5, has rational growth in one generating set, but transcendental in another. This is, I don't know, very cool, very perhaps surprising result, especially because it's the standard generators that have transcendental growth. And what he shows is that a certain cubical generating set has rational. Okay, so you have to be super careful. And even for two-step nilpotent groups like H5, it's not the case that they all are going to have rational growth in all generators. Okay, so here's that formula that Shapiro and Benson gave in the 80s that actually, here I've written down the spherical growth function of the Heisenberg group in standard generators. It's this particular degree 3 polynomial. Notice, though, it's not exactly polynomial. It's instead something called a quasi-polynomial. It's periodically polynomial, in this case with period 12. So as a cubic, it's got a fixed leading coefficient, next coefficient, and next coefficient, but its constant term oscillates with period 12, which is kind of cool. Okay, so as I said, these are called quasi-polynomials. And it's a fact that if a sequence is bounded by a polynomial, then being eventually quasi-polynomial, so for large enough n being periodically polynomial, is equivalent to rational. Okay, so this shows rational growth for the standard generators. Okay, so then there's these two theorems with two different collaborators where I was trying to think about this sort of problem with the tools from CC geometry. So first with Chris Mooney, we studied the lattice counting problem, thinking it might help us build up to growth, and showed that for any generators, the number of lattice points in the CC ball is quasi-polynomial. So that's suggestive of rational growth for any generators. And then 5 years later, with the same Mike Shapiro who had done this formula above, we showed that it works for any generators. In other words, you get rational growth in Heisenberg for any generators. So I want to spend the next 10 minutes or so explaining the ideas behind this, because I think they really illustrate this discrete continuous bridge that you walk back and forth with care. Right, so again, it was of course known that the group growth was bounded above and below by polynomials, but this shows that it's on the nose. What we prove shows that it's on the nose quasi for any generators. Okay, so just as a quick summary then, it was known already that hyperbolic groups and virtually abelian groups were what Mike and I call pan-rational, rational for any generating set. And it was known because we really understand their geodesics. Lots of groups are in this kind of middle category where you know for at least one generating set that they're rational. And so this theorem I just cited moves the Heisenberg group over into the left-hand column where you know it for all generators. I'll just mention, because it's nice, that Thurston also observed that there are various kinds of groups, those with unsolvable word problem and those of intermediate growth, for which there's no generating set that makes them rational. So there's this kind of interesting collection of possible positions here. There's lots of papers that kind of explore the middle category of being rational for at least one generating set. So I won't go into it, but just say there's kind of a big industry. But that left-hand column is incredibly small. So I believe, and please anyone here tell me if you know otherwise, this is the full list. Hyperbolic groups, virtually abelian groups, and now the Heisenberg group, the 3D Heisenberg group, are the only things known to be rational for all generators. Yeah. Okay. So let me sort of say what the ideas are that go into how to prove this. I'm certainly not going to try to give a complete proof. It's obnoxiously technical in places, but it does have some ideas that are easy to communicate, easy-ish. We'll see. The idea is partly to think about, there is no regular language of geodesics in the Heisenberg group, but there are nice languages that we call shapes and patterns that really relate to sort of how geodesics look. And those translate to languages for the group theory. And then we show that there are what we call rational competitions that determine which shape or pattern is going to be the shortest way to get to a particular group element. Enumerating spellings by length, once you have a shape or pattern, is a rational function. And so there's sort of rationality in every direction, and you add it all up and get a rational function. Okay, so finite collection of languages, rational calculation to decide which one is the right one to get to a point efficiently, and then rationally, finitely many ways to do so, enumerated by a rational function. Put it all together and you get a rational function. Okay, so let's see, I'm just keeping an eye on the time. Okay, let's try to be concrete with the chess knights again. So here, consider the part of the picture that you're
Moon, can I ask you a question to
Yes.
understand if looking at your picture, right? So at some point we take the ball, the discrete, the word ball of radius n, and we know that this is inside the ball of radius n with respect to the norm. But initially you have some holes, correct? But sometimes, for example, for some metric like the L1 metric, then they actually coincide in the sense that one ball is exactly the lattices intersect with the ball. What you are discussing now, is it related to the possible fact, which I'm not sure if it's true, that for any generating set, eventually the balls are the same?
Which
So
balls?
the word ball, the nth ball, the ball of radius n in the word metric is exactly the intersection between the lattice and the ball of radius n in the sub-Finsler metric.
I don't think that's actually true that they're eventually identical, but they're eventually off by only at most a finite number. There's sort of, as you know, there's this kind of bounded difference. The same way I mentioned earlier that, generally for nilpotent groups, just that the ratio of CC length and the word length goes to 1. But you don't necessarily know bounded difference for all nilpotent groups. That's an observation of Emmanuel's. But for Heisenberg, you do have bounded difference.
Yeah.
So I think what that translates to in the geometry is you might not have that the points inside a certain dilate of the, inside the CC sphere. You might not have that all the points inside that are identical to the points in the discrete ball, but they're only off by finitely many, and that's good enough for these counting problems.
Okay, but what you are saying is stronger than what Stoll was saying, that the difference is bounded, no? You are saying something stronger.
Is it stronger? Actually, bounded difference is good enough to prove everything I want to prove. So I think of what I'm doing here as like an application of bounded distance, not a strengthening.
Okay. Okay, thank you very much. Well, thanks.
Yeah. No, thanks for asking a question. Otherwise, I feel like I'm just talking to my screen. Okay, so let's work through this example just very briefly. So you see here a picture of the chess moves, and let's look at the sector that's bounded by that's shown here, that's bounded by the direction 2, 1 and the direction 1, 2. Okay, so that's given by these inequalities, and it's not quite the case. So look at 2, 1 and 1, 2. Those are the 2 yellow points down there in that sector. It's not quite the case that combinations of these reach everything. They reach the points on the lines, but not the points between the lines, if you look at my picture. I hope that's clear what I mean by that. But 2 of these adjusting moves, if you can sort of just adjust over to start at 1, 1, or if you can adjust over to start at 2, 2, that's enough. Now from those, you can get to everything. So what I'm saying is that these 3 patterns suffice. You can do some A1s and A2s, or you can start by prepending A3, A8, and then do A1s and A2s, or A3 squared, A8 squared, and then do A1s and A2s. So just all I'm saying is these 3 patterns of words get you everywhere in this sector. Okay, so I can think then about these as affine functions that take these patterns, these 3 patterns that I just described. I can compute the length of the word once I fill in the stars, and I can compute its position in this very simple way. Okay, so how do I figure out which one I need to get to a particular point? In this case, it's not hard to see that it can be decided by just checking the congruence class of A plus B mod 3. That's if you stare at this for a second and do a little calculation, that's enough to decide which of these 3 types you have. Okay, so this is the theme that I claim holds for all generators here. It's that you can kind of run this rational by looking at linear equalities, linear inequalities, and congruences. That tells you everything you need to know to figure out how to reach a point geodesically. Okay, so I can actually write that down as if the pattern's called W, GWN will be the points for which W is the winning pattern to reach that point, and I can get there in length. And here I can just be perfectly explicit about what that is if I work through this example. Okay, so this sets us up to use a really absolutely gorgeously beautiful theorem of Max Benson's that I think is probably too little known and that more people should exploit. So here's how it goes. Let's say that an elementary family in Z to the D is some family defined by finitely many equalities, inequalities, and congruences. So I've written here what that looks like. I've got some equalities, inequalities, And that is exactly what we had on the last slide. We saw that the positions for which some particular pattern is winning at a particular length is just given by exactly this, equalities, inequalities, and confidences. Okay, so Benson goes on to say, let's say that a bounded polyhedral family is a finite union of finite intersections of these. And then here's the theorem, which I think is really fantastic. He says, if you have any polynomial over a bounded polyhedral family, then if you add up, take a look at the sum that's written here. If you add up over the points in this polynomial family, the values of that polynomial, you get a rational function. Just quickly, I'll say, looking at that, that might sound really obvious if you're not kind of tracking it too hard. But just to see, if you think about it, if you choose to think about this later, and you want to see that this is kind of deep, just note that you cannot exchange the roles of linear and polynomial here. You'll get a false theorem. So if you try to add up linears over a polynomially defined family, it will no longer be a rational function. It matters that it's polynomials over a linearly defined family. So there's something a little bit deep here. Okay, so this is what I want to use. How do we use it? An immediate application of this isn't how Chris and I were thinking about this in 2014, but in retrospect, this immediately proves our theorem that the number of lattice points in these CC balls is quasi-polynomial. Why? Because remember the structure of these were given by piecewise quadratics over polygons. Boom. Benson's theorem finishes it and says that it's given by a rational count, so it's eventually quasi-polynomial. Okay, that's basically exactly what I just said. You end up just adding up over these quadratics, over these polygonal pieces, a count that's just quadratic. Okay, another application though is going to be rationality for the Chess Knight growth function. So recall that we were able to write down this set, and if you add up over all, there's only finitely many patterns, and if you add up over all the patterns, the counts that you get this way, you have an expression that looks like what's below. And once again, this is summing over a polyhedral family. You apply Benson's theorem and you learn that this is rational. Okay, we're not doing this so far. What I've written here doesn't do rationality in the Heisenberg group. This is just recovering a special case of rationality in the free abelian group. But it's a kind of, it presages how this is going to work in Heisenberg. Okay, so certainly don't have time to go through all the details for this, but just to give an idea. So there's kind of 4 pieces that you need to make the Heisenberg case work. You need to not only understand these Boozman polygons for the isoparametric formulation, but you need to understand how quickly the area falls off once you start just sort of relaxing the shape. So that's a kind of balancing lemma that you need. And then you need to understand that the area type elements can be geodesically represented by something that's close to a CC geodesic. And then the same thing for the norm type. Those group elements can be geodesically represented by something close to a CC geodesic. And finally, just a competition lemma that says, when you're trying to decide which shape or pattern to use, that is determined by finitely many linear inequalities, equalities, and confidences. Now, these are the ingredients that make it work. There's a few subtleties that I thought might be interesting for this crowd. So please note what I'm not saying. I'm not saying that word geodesics always fellow travel CC geodesics. They may not. There are word geodesics that are far from any CC geodesic. But what I am saying is that every group element is represented by some word geodesic that does. And so this actually takes some care to prove, but it's a little subtle, but it turns out to be quite useful for lots of group theory applications. There's another subtlety that I probably don't have time to talk about, but that I think is kind of interesting, which is notice that the length and the shape, as we saw, are affine functions of the inputs, but the height is quadratic. And this is a problem for the argument because we can do rational competition, but we don't get to check a quadratic equation. And so we have some sort of idea for getting around that by looking at differences in quadratics so that they can be checked within the framework of rational competition. Okay, then finally you get to put it all together. So for the walls, that is for these norm type geodesics, you just add up over shapes and length and slack in the length that comes from this bounded difference, Enrico. And then finally the positions at which the shape wins, and presto, you have a rational function. And for the roof, it's similar. You have patterns, you have their length, you have some slack in the length. You have these positions that can be reached by each pattern, and then quadratically many that can be reached in a winning fashion. And so once again, you win because you end up summing quadratics over these polyhedral families. And this is how everything fits together. Okay, so I'll just, I'm essentially done. I'll just give a little tiny tour of other things you can do with this general pile of methods, and then I'll be done. Okay, so what are some applications? So here's some things we like to think about in geometric group theory. We like to ask about asymptotic density. If you take a large ball in the Cayley graph, how often does something happen? So for instance, what share of the points can be reached with stable geodesics? How frequently is do you see subgroup distortion? Lots of different kinds of questions like this. The point here is that we can turn those geometric by integrating over a ball. Okay, let's see. So this is, I can, if anyone's interested in following up on details, here I'm sort of gesturing at applications, but there's a whole collection of papers that do this kind of thing, and just please reach out to me if you want particular examples. Here's the kind of question that people ask in group theory, almost convexity. Is it the case that for points on a certain sphere, you can connect them inside the ball by a path that's not too different from their geodesic? And yes, that works here, and it's just an application of bounded difference. So you sort of figure that out in terms of the CC geometry, and then observe by taking the bridge from continuous to discrete that the same argument carries over to the discrete world. Sprawl, this is a question that I enjoyed thinking about for some years. What's the average distance between 2 points in the sphere? Okay, well, you can get that kind of quickly here by taking advantage once again of the understanding of the limit shape. So you use a kind of limit of counting measure on the limit shape, and you can sort of get bounds on this. Dead ends. So there's a nice paper from, I don't know, 10, 15 years ago that finds what geometric group theorists call dead ends in the discrete group. And we already saw, of course, there are dead ends in the CC geodesics. And if you're able to sort of use this description relating word geodesics to CC geodesics, you get an argument that circumvents 25 pages of combinatorics to see that the discrete group will also have dead ends. So these are the kinds of things you can do. Horofunction. So I think the next talk is Nate Fisher. And he'll be talking about some really nice work with Sebastiano, where they think about horofunctions, and it uses in part, I mean, it uses many things, but it uses in part these kind of ways of going back and forth between continuous and discrete. So I hope you will enjoy hearing about that next. Just two more little things that I think are cute, and then I'll be done. Another one is curvature. So you can define a discrete analog of Ricci curvature, actually following some ideas of Jan Olivier from the early 2000s. And what's nice about Ricci curvature definitions applied to groups is that they're kind of medium scale. Nothing needs to go to infinity to define Ricci curvature, but they're also not infinitesimal. So they're this kind of nice sort of macro curvature that you can define in discrete groups. And you can sort of write down how this works, and using these same kinds of ideas, going back and forth between discrete and continuous, you can make some nice observations by dividing up the kind of walls and roof and thinking about them separately. And what it will turn out is that positive curvature points, zero curvature points, and negative curvature points all exist with positive density in the Heisenberg group for any generators. So that takes advantage of this kind of geometric apparatus. And then the last one, which I just think is nice because it's surprising. It sounds like it's from such a different world. You can also get leverage on equation solving in groups using these kinds of technologies. So generally, the equation problem is if I write down some equation with constants and variables over a group, is there an algorithm that can sort of tell you yes, no, whether solutions exist? If I give a single equation, if I give a system of equations, if I give a system of equations and inequations, not inequalities, but like non-equations. And so you can do this in Heisenberg. And what you find is that single equations are decidable, but systems of equations are undecidable. And how do you do this? You reduce solvability to quadratic equations over lattices. On the other hand, the undecidable comes from showing that systems can encode arbitrary polynomials, and then you quote Hilbert's. Okay, so here's what I think is maybe a final and unexpected application of this way of thinking about the discrete continuous bridge, and I'll stop there. Thanks.
Thank you very much. Are there any questions?
I have one. Hi, Moon. Here is Pierre Pensu. How
Hi,
are you?
Pierre. How are you?
So what do you mean by there exist word geodesics which do not fellow travel any CC geodesic? What does this mean exactly?
So this picture shows an example. So you can, okay, so first, I'm sorry if, yeah, maybe this wasn't perfectly clear, but I'm sure it wasn't. But one thing that I have in mind is, so how do I even talk about whether word geodesics, which are after all just strings of letters, what does it mean for them to fellow travel a CC geodesic? So what I'm doing is I'm thinking of the Heisenberg group, the real Heisenberg group, as like R3 given by exponential coordinates, say. And so now we know what it means to draw in that space a CC geodesic, right? It has a particular kind of way of moving through that space where exponential coordinates, again, represent what's happening in the group. So now the discrete Heisenberg group sits as a lattice in that space. And so if I have a spelling in the discrete group, that's a sequence of lattice points. And so first of all, what I mean by fellow travel is just that sequence of points stays boundedly close to a certain CC geodesic. So I probably should have said that earlier, but that's what I mean by fellow travel in the first place. Okay. That makes sense? Okay. So, but then there are examples, and I've drawn one here, where you can have a word geodesic that follows a rectangle, and that rectangle has some eccentricity. So there is no CC in this particular picture. I'm thinking about the L1 norm, the standard generators. And so we know that CC geodesics have to be squares. They can't be rectangles of some other eccentricity. They have to be squares. But it's possible for a word geodesic to follow a rectangle. And so there is no, and I can do that at any scale. I can make really big ones. And so they're not within bounded distance of a square. However, in this case, what you can see, what I've done in this picture, is that there's a way to take that gamma, which is the word geodesic following a rectangle, and apply a sequence of kind of reductions that change it to first a gamma 1 and then a gamma 2 that does stay close to a square. So the punchline here is that even though whatever word this was is geodesically represented by this rectangle, it is also geodesically represented by a near square. Does that make sense? Do you see what I mean?
Okay. Okay, I see. Thank you.
Any other questions? Yes.
I have a question regarding the definition of being quasi-polynomial, because you said it's related to then the rationality of the growth theory. So my question is, can you get meaningful definition if you allow other coefficient to be periodic other than the first one? And if this then translates to another other properties of the growth theory?
Oh, yeah, I love that question. Okay, so first let me say, these are, where's the one where I actually write down? Okay, so here's the slide where we actually see the spherical growth function for Heisenberg with standard generators, and it's already got period 12. So when you go up to hex, the period jumps to 60. And hex is the next simplest generating set as far as I'm concerned. So actually doing computations with these gets really obnoxious really fast, is one thing to say. So I was very curious about exactly what you just asked, which is which coefficients can oscillate. So we know that the top coefficient can't oscillate because it's given in the ball version, it's given by a certain volume, and in the sphere version by a certain surface area. So this can't oscillate. And I think we also know that the next one can't oscillate, and everything else we don't know. So I don't have examples where the non-constant terms oscillate, but I'm fairly sure it can happen. So to relate this back to Ehrhart polynomials, so let me find some slide that has Ehrhart polynomials on it. Yeah, so here you can see I've got a number of these Ehrhart polynomials written out for these shapes. Again, the Ehrhart polynomial is just the lattice point count inside dilates of a shape. So if I have a shape omega, then G omega n is the number of lattice points inside the n times dilate of omega, right? And these are thought about a lot by algebraic geometers, in fact, because in a certain sense that I could not explain because I don't know it, they enumerate toric varieties, and you know that's the phrase that algebraic geometers cite as to why they care. So these are well studied, and in that world, this also turns out to be an interesting and difficult question. So for kind of the same reason, the leading terms here are just the area or volume of the shape. The second term is a surface area. It turns out that the constant term in the Ehrhart world is given by the is a topological invariant actually of the shape. So these actually work whether or not the shape is simply connected. The shape can have some topology, and we know that the constant term is a topological invariant. It's related to the Euler characteristic, but the rest are not understood. And there are a bunch of nice papers trying to kind of read off meaning from these other coefficients, sort of the same way that that the trace formulas work in other contexts of counting problems. So back to your question, I spent some time thinking about the numerology of these quasi polynomials. And didn't get very far, so a lot is open, and it would be quite interesting to see what else you can sort of read off of these numbers. I do think they're probably meaningful, but I don't know what they mean.
Okay, thanks. Then I have another question. So could it be that in other nilpotent groups you have so you have oscillation of coefficient that are not periodic?
Yeah. Well, in particular, what about H5, Stoll's example? So take H5, the higher Heisenberg group with standard generators, and you know that you have transcendental growth. He actually shows that it's transcendental. So what does that mean? Well, it's still bounded by a polynomial, right? So I should say just really quickly, because for me, this was hard to, when I started thinking about this was hard to understand. How could something be bounded by a polynomial and still be kind of behaving weirdly and transcendentally? And so just a simple example is like, imagine the sort of digits of pi sequence, 3, 1, 4, 1. So that's bounded. It's bounded by 10, but it's not oscillating in any nice way. So something like that must be going on with the with H5 and standard generators in order that it's polynomially bounded but still behaving transcendentally. So yeah.
Thanks.
Okay, folks, I think we're going to start again. I noticed just before standing up to introduce Nate Fisher that you might think we're related, but as far as I know, we're not. But it is a pleasure to introduce Nate Fisher, who's going to tell us about Horofunction boundaries and homogeneous groups.
Can you hear me? Okay, I think so. Thank you. And thank you to the organizers for putting together this great conference and for providing me with this opportunity to speak. Oh, this moves. And so I forgot to write it in my abstract, but this is joint work with Tullio de Mars. And it's building upon some previous work with Sebastiano Nicolucci Golo, as Moon mentioned. Yeah, and so Moon already described what this is, so I don't have to. But as part of my PhD, or during my PhD, I created some of these animations for different spheres. Let's move this mouse. And while I won't talk too much about this like sub-Finzer setting, I wanted to include the picture because I imagine several people here would be intrigued by it. Cool. And so what is the motivation? Like, what is the main idea behind this talk? And it's kind of, in a vague way, work towards showing that the Horofunction boundary is a quote-unquote good boundary for nilpotent groups. Something that Tullio and I have been thinking about is, like, we want to show that for at least a certain class of Carnot Lie groups, we can see that the Horofunction boundary is full dimensional. It's codimension 1, which in a way is telling us that we are seeing everything in our space. And this is building upon an idea from the project with Sebastiano that we can get a correspondence between points in the unit sphere, which we can kind of think of as asymptotic directions in our group, asymptotic ways that we could travel off to infinity. So we get a correspondence between those points on the unit sphere and points at infinity in the boundary, kind of like providing a directionality at infinity. And kind of related, but not super related, is this conjecture first suggested by Carlson, and I think written down by Duchin and Yaden, that a finitely generated group equipped with a word metric has countable Horofunction boundary if and only if it is virtually nilpotent. I just think that this is an interesting conjecture, and it would also kind of provide evidence towards this vague statement that the Horofunction boundary is kind of a good fit for nilpotent groups and like can detect polynomial growth. And I will say that Duchin and Yaden have shown that this is true for groups of linear growth, and that's as far as things have gone so far. So there's plenty of work to do to prove this conjecture. Great. And so we'll be thinking about homogeneous groups in this talk. And so we'll let G be a simply connected graded nilpotent Lie group. We will often, but not always, assume that G is stratifiable and equipped with its Carnot grading. And with this grading comes along a family of dilations, and we will choose metrics on the group which are homogeneous with respect to those dilations. So for example, we have the family of filiform groups, which we can define via their Lie algebras. And so we'll look at these m-dimensional Lie algebras of step m-1 graded. So the okay. Oh, so grading, you can define a grading on a Lie algebra where the first layer may not bracket generate the rest of the Lie algebra. Yeah. Any other questions? And so for these filiform Lie algebras, we'll have m basis vectors with the only non-trivial bracket relations being the bracket of x1 and xj is equal to xj plus 1, which induces this stratification, this Carnot grading. And we've seen examples, some of our favorite examples live in this category. And so we have the R2 and the Heisenberg group as the first two filiform groups. And so we can see these filiform groups as another way of generalizing the Heisenberg group. Cool. And so what metrics will we consider? And so here's another picture, but of the unit sphere that's on some t-shirts in the audience. And so as a geometric group theorist, I would be happy to study the metrics that arise as asymptotic cones of finitely of word metrics on the discrete groups. But for the higher filiform groups, I'm not sure how much is known about that that type of geometry. And I, for one, am not. So I think things are a little complicated. And so instead, we will look at another class of metrics, quasi-norms and metrics. And so just for notation, first we have these projections, pi sub j. We'll take a group element and project to the v sub j, the jth subspace in the grading. I guess grading on the Lie algebra, not the group itself. But in exponential coordinates, we can kind of go back and forth between those two. And we'll have these two homogeneous quasi-norms. And what is the, I think this, okay, yeah, we have a pointer. And so we will, in both of these, the definition is pretty similar. And so we will take our group element and project it to each one of the layers of our grading. And then on each layer, we will take, in this case, the L infinity norm, in this case, the L1 norm, restricted, like, yeah, just looking at each layer individually. And we have to take a root to guarantee that things maintain, are homogeneous. And then once we have done that for each of the layers of our grading, we take the max. And so these are two different quasi-norms that we can define on an arbitrary graded group. And I will say that in the filiform groups, all of our layers are one-dimensional except the first one. And so really what we're looking at in the filiform case, we have the L infinity or L1 norm on just the first layer of the stratification, and then everything else is like a sup norm. Cool. And there's nothing super special about L infinity or L1 here. We could have chosen other norms and defined similar homogeneous quasi-norms. Great. And so in general, these quasi-norms may not satisfy the triangle inequality, so they may not induce metrics on our group. And we're going to be looking at Horofunction boundaries. And so we do want actual metrics. Fortunately, there's a lemma of Gavarch that says that as long as we are stratified, as long as we're dealing with a Carnot group, there exist coefficients, a decreasing or non-increasing sequence of positive coefficients, such that we take those quasi-norms and just throw in these coefficients, and things satisfy the triangle inequality, and we're all set. And so without too much work, we can pass to genuine norms, which induce genuine metrics on our groups. Cool. All right. And so I don't think this is a slide for like a more general audience. I don't think I need to convince most of you here that boundaries are worth studying. But in the world of geometric group theory, there's a rich theory of boundaries. Boundaries can be used to derive a wide variety of results from algebraic, dynamical, and geometric points of view. But some of that theory doesn't work quite as well in nilpotent groups. And so an example that we've seen already this week and in Luca's talk just today, the visual boundary is a commonly used tool. And I'll take the second definition that Luca just mentioned today, where we can look at equivalence classes of base-pointed geodesic rays, where we say that two geodesics are equivalent if they have finite Hausdorff distance. And as Moon just mentioned in the Heisenberg group, many geodesics are finite or run into dead ends and cannot be extended to finite rays, infinite rays. And also, geodesics are not always unique, and that can deal with the topology of the visual boundary. And so an alternative is the Horofunction boundary. And to define the Horofunction boundary, we'll take our metric space and we'll embed it into the space of continuous real-valued functions on that metric space. So we'll fix a base point, x naught, and then we define this embedding iota by taking a point in our metric space and sending it to the function, which first computes the distance between our point x and some input variable, and then we subtract away the distance between x and x naught. So then we're in this function space. We can take the closure under the compact open topology, and we define the Horofunction boundary to be any new points we get in the closure that weren't already there from the embedding. Great. And some nice properties of the Horofunction boundary. So the construction is very general. There are no assumptions on the geometry of our space. And so we can use this in a wide variety of groups and spaces and get like nice compactifications with very mild conditions, under very mild conditions. And the isometries of our metric space extend to homeomorphisms of the boundary. And so if you want to study dynamical properties of isometries, this is a nice place to look. Cool. But one downside of the Horofunction boundary, it is not very rigid. People this week have been talking about QI rigidity, and that is not something that we have here. The Horofunction boundary is very sensitive to the metric, by no means a QI invariant. And just a basic example to get us started. So we can take the plane with the L infinity metric, and the visual boundary setwise is equal to the circle, because in the sup metric, straight lines are geodesics. And so we get all of the points of the circle that we would kind of expect as points in the visual boundary. But geodesics are not unique. And so these two green geodesics on the right and the two blue geodesics on the left are equivalent. And so you can play around with the fact that geodesics are not unique to see that the topology collapses and you end up with a trivial topology. You get a non-Hausdorff boundary, which might not be very pleasing to you. But if we go over to the Horofunction boundary instead, we get the same set of points really in the boundary, but the boundary is homeomorphic to the circle with its standard topology. And this is a picture from a paper with Moon. And so these are the different functions that you get in the Horofunction boundary. I'll just note that we get these like 4 coordinate functions, and then everything else can be just written as a max of plus or minus x and plus or minus y, possibly with this parameter m, which will just be some positive number that's kind of, not important, but we end up with a bunch of like max functions. All right. And so what else is known about like these boundaries and these, I guess we're not in the filiform case yet, but other nilpotent examples. So for the sub-riemannian distance metric on the Heisenberg group, I'm not sure who this theorem is attributed to, but the visual boundary of the Heisenberg group with the sub-Riemannian metric is homeomorphic to a circle. And so that's great. It is still homeomorphic to the circle, but we're in a 3-dimensional space. A 1-dimensional boundary maybe isn't too satisfying, kind of makes me feel that like we're missing something in this boundary. We're not seeing all of the space. And then a theorem of Klein and Nikas says that the Horofunction boundary of the sub-Riemannian metric on the Heisenberg group is a 2-dimensional closed disk. And so here we have a picture of the unit sphere and the Horofunction boundary colored in a way to like show a correspondence between points on the sphere and points at infinity. And so here this North Pole is colored purple because if you travel straight vertically up, you will end up somewhere in this disk. And if you kind of perturb the way that you travel up vertically, you can end up in different places in this disk. So we kind of see that the non-smooth points, this kind of cusp at the North Pole that we've seen, the Horofunction boundary notices that things are not very smooth there. And so you can really, the Horofunction boundary kind of blows up there. And the last thing to note is that there's a vertical collapse. You can't see it here, but the South Pole is also colored purple. And if you travel straight vertically up or straight vertically down, you'll end up at the same place in the Horofunction boundary. So this Horofunction boundary can't really distinguish whether you're traveling up or down. And then with Sebastiano, we looked at the Horofunction boundary for these polygonal sub-Finsler metrics arising as asymptotic cones of word metrics on the integer Heisenberg group. And we get a similar picture, but things are a little bit more complicated. We still get this disk's worth of functions coming from the north and south pole. But when we look at the non-smooth parts of this sub-Finsler sphere, we get a lot more functions in the Horofunction boundary. And maybe it's not super clear here, but on each edge, there's a green sphere and then a blue sphere attached to each edge of the polygon. And so, yeah, we have a lot more functions than what we saw in the sub-Riemannian case, telling us that things are definitely not the topology of this Horofunction boundary is not a QI invariant. But we still get this way of kind of thinking about the Horofunction boundary and getting a correspondence between points on the sphere and points in the boundary. And this is what Tully and I set out to try to generalize. Can we get similar results in other Carnot groups? And fortunately, we could. And so this is still work in progress. Hopefully we'll be on the archive very soon. But if we consider the m-dimensional filiform group with its Carnot grading and equipped with either the homogeneous sup norm or the homogeneous taximax norm that were defined before, and we're pretty sure, I didn't write it on the slide because it's something we just thought about. We think, remember that these norms are mostly just sup norms, but on the first layer, we were choosing a different norm on the horizontal plane. We think we could replace that with most other norms and things should still work out. But what's the result? The Horofunction boundary of this group, first of all, is made up of functions which are piecewise linear or linear, like actually linear or piecewise linear, and strictly in the horizontal coordinates coming from the first layer. And also they are m-1 dimensional. So we're getting full dimensional boundaries in all of these cases. And so that's nice because now we have, for any dimension and for any nilpotency step, we have examples of Carnot's groups whose boundaries satisfy these conditions. Great. And is this surprising? And so we, in the course of looking at all of these groups, we computed the Horofunction boundaries of a bunch of different examples. And there are examples of stratifiable groups where we chose non-Carnot gradings. And we got boundaries which were of codimension greater than 1, where Horofunctions were nonlinear, where the Horofunction boundary was not necessarily compact. And so things can go wrong. And just a little note here that sometimes the homogeneous norms we were looking at with these non-Carnot gradings are quasi-norms as opposed to genuine norms. And so they might not be inducing actual metrics. And so maybe there are a couple of things that were leading to these strange, or strange examples where things kind of went wrong. Yeah, question. So in this case in particular, we were dealing, I think we chose the Heisenberg group with the grading 1, 2, 3. So we were putting a quadratic dilation on Y and a cubic dilation on Z. Okay. Which functions? Oh yeah. Yeah, and so we're no longer dealing with a metric, and so we're not guaranteed. We don't have the triangle inequality, and so I think that might also be where things are going wrong. And so with the remaining time, I'll just say a little bit about how we some of the ways to get to this point and prove what's going on. And this is coming from what we thought about with Sebastiano. And so if we have a point on the unit sphere of one of our homogeneous metrics, we'll take epsilon of n to be a sequence of positive numbers going to 0. And we'll look at points q sub n, which are dilates by 1 over epsilon of n of that unit point on the unit sphere. And so this sequence q sub n is going off to infinity. And so then when we take that point q sub n and embed it into the space of real valued continuous functions, we get, like, just by definition, this is what we're looking at. And then we can use left invariance and homogeneity of the metric to rewrite this difference in this form. And so when we're taking the limit of a sequence of iota of q sub n, we get a limit of this form. And so this looks like and very much is a derivative. And so Horofunctions, studying Horofunctions can really come down to studying derivatives of the metric at points on the unit sphere. And that's what we call the key, like a key lemma in the paper with Sebastiano, that every Horofunction in the boundary of a homogeneous group can be expressed as a limit of this form. Notice now that we're also letting p sub n vary. And so it's not necessarily a derivative exactly, but kind of a generalized derivative. And at points where the metric is smooth, this derivative is the Ponceau derivative. And at non-smooth points, where the metric kind of like changes in weird ways, the understanding these types of limits requires a bit more work. And what goes into that work? And so we can use this lemma to unify some differently derived results in other settings, Euclidean space, polyhedral Minkowski spaces. You can kind of recover the results, some results that were already out there using this point of view by looking at the unit sphere and studying these derivatives. And so what's going on in this, like in this non-smooth case? How do we understand these types of limits? And so a baby example, let's assume that we are in the plane and we're looking at the sup norm. That sup norm can be defined in different ways depending on where you are in the plane. And those 4 cones are really just the dilation cones of the faces, which in this case are the edges of the unit circle for the sup norm. And now let's just choose a point P on our like at a non-smooth part of our circle, and we want to understand what type of what we get when we look at this limit. And we note that depending on what our point V is, how we compute this distance, how we compute this distance will depend on what the point V is, because this is just a point that's slightly pushed off of P, but it could be slightly pushed off to P into the green direction or into the blue direction. And in the abelian case, it's not too hard to see that, okay, if P times delta times the dilation of V is in omega, here we'll just take omega to be this blue region on the right. If P times the dilation of V is in omega for epsilon sufficiently small, we left translate, we dilate, and we see, okay, V then is in is in this blue region defined by y being less than x. And so yeah, again, in the abelian case, this isn't so hard. It's not necessarily more difficult, but it can get more complicated in higher step nilpotent groups where left translation and dilation can both cause things to like twist and bend. And so when we compute this limit, we like kind of plug things in, and in the end, that's how we can recover that we get the max between x and y as the derivative of the metric at this corner point. Great. Cool. And so this is just the result again, that really what we wanted to say, like what we're able to show is that the functions are always piecewise linear. They're always can be expressed as functions of variables or coordinates coming from the first layer of our stratification. and that the boundary is full dimensional. And so what were the main obstacles here? And so the first was that we needed to be able to compute what this distance is, which meant that we needed an understanding of this product. But multiplication in exponential coordinates, it comes from the Baker-Campbell-Hausdorff formula, which gets super complicated when you look at nilpotent groups of higher step. Fortunately, though, we were able to, when we were taking a closer look at how Horofunctions are computed, we realized that we can restrict our attention to just certain types of brackets in the Baker-Campbell-Hausdorff formula. And those brackets are better understood. We know that the coefficients of those brackets in this formula are related to Bernoulli numbers. We were able to make use of this kind of simplified version of the Baker-Campbell-Hausdorff formula that we needed to pay attention to get what we wanted. And then the second obstacle was to analyze the blowups of the metric at vertices, edges, and other higher dimensional non-smooth parts of the sphere. And we were able to see that there's at least one face of codimension 2 on the unit sphere associated to a family of horofunctions of dimension m-1. And so, yeah. And I think that's all I wanted to say here. This is the homogeneous sup norm ball in the Heisenberg group, so L3, and this is its associated horofunction boundary. And yeah, thank you.
Are there any questions?
So one question, you mentioned that in this filiform case, you needed to somehow use that the Baker-Campbell-Hausdorff formula, the coefficients you get are related to the Bernoulli numbers. But I didn't really understand what you mean by this comment, because the Baker-Campbell-Hausdorff formula is, in the general case, defined by a recursive formula that's with the Bernoulli numbers as coefficients. So there's nothing specific to the filiform about the Bernoulli numbers.
Right. And so I guess I'm thinking of it like there's another definition of the Baker-Campbell-Hausdorff formula where it's written out explicitly. And for certain type of brackets, those which look like X. Yes. We know that the coefficient here is just a Bernoulli number of divided by some exponential, like some, yeah, I guess like 2i divided by 2i factorial. And so, yeah, what I wanted to say is that like it really is related to the Bernoulli numbers.
So it's not enough in the, like, to use the general recursion formula? So...
I guess we wanted to be able to like get some bounds on what these coefficients were. Yeah.
All right, thanks.
Yeah.
Thank you. Could you show us again Carlson's conjecture? I wasn't aware of this.
I don't know if this is the best way to get there, but there it is.
So do I get it? What does countable mean here? Because all you've shown are really continuous, right?
And so this is for finitely generated groups. And
yeah, what you showed are for the Lie group. I see.
Yeah. And so
when you go to a countable subgroup, I see you find only discretely many points.
Right.
I see. Thank you.
And there I have a question. How can it be compact?
Well, 1 over n.
No, I understand that example. So it's very non-homogeneous somehow. It would accumulate at finitely many points.
Right.
Okay.
Yeah. So yeah, I think
Yeah.
Say it again. Yes. Ooh. That I'm aware of, I don't know. I don't think either direction is.
I would like to go back to this fact that you're saying that the boundary may not be compact, and because I understand that this the Horo boundaries, the Horo functions come as tangents of the sphere, where you might also change the points, and we know that for some Carnot groups, the spheres might form cusps, and because of abnormal curves. But you have them already in the angle group, which is a filiform group. So it's not really a problem of not being Euclidean differentiable for the distance,
right?
The lack of compactness.
Okay.
So on the one hand, I don't understand why there are groups on which you don't have compactness, and why this is already not happening in the angle.
Okay.
Can you convince me that?
I don't know if I can right now, but I'd be happy to talk to you about it.
Okay. Thank you. Thank you anyway.
Thanks.
Anybody else? If not, let's thank the speaker again. Hi, everybody. Welcome to the last talk of the workshop. It's a pleasure to introduce Assaf Naor from Princeton, who's going to tell us about the inverse problem for isometry groups of norms.
Okay, thank you very much, and thank you very much for the invitation. It's actually my first time in Pisa on an academic trip, not as a tourist, and it's a great pleasure. I know this is the last talk of the conference. I think we should start by thanking the organizers for everything. Also, it's the last talk, so many of you are tired. I'm gonna do some basic things. Stop me if I go over time. I think one little contribution that I made, Giovanni and I made, is when before all of you came in, we fixed the clock. We took it down and fixed it, so I'll be able to know the time. But that clock wasn't correct. Okay, so at least something good came out of this. Okay, so I'm not gonna. So all the new results that I'm gonna present here are joint with Emmanuel Boyard, Martin Liebeck, and Aluna Rizzoli. And I'm not gonna give the list of authors because without exception, all the new results are from this joint paper. And my goal here is to do a gentle introduction to an old question. It's really an old school inverse problem that I think probably is very likely different from what all of you are used to thinking about. It's certainly different from the kind of things that I do, which always have big errors. This is about isometries. I did get interested in this because of a question about some by-Lipschitz invariant, and I might explain that motivation in the break for those who want to know, because it just got a life of its own, and it's not related to that. It's really a question about isometries, but it's really an old, like a very basic kind of question that appears all over mathematics, which is if you start with a normed space, or let's say Banach space. So I'm going to think of Banach spaces as metric spaces. So I only care for now about spaces over the real line. These are metric spaces. So of course you can associate with the isometry group, right? Which is all the isometries let's say that fixed origin. All the isometries F onto that fixed origin. So by the classical Maslow-Ulam theorem, we know that this is always a subgroup of GLX, So this GLX, it depends just on the topology induced by the norm. So by that I mean that all the operators from X to X that are 1 to 1, onto, and bounded, which means that their inverse is bounded by the open mapping theorem. Okay, so so this is a group of that is associated to when I give you a norm, a Banach space, I get a group, and the question is, what about the inverse? Can we, if I give you a group, so the inverse version of this, given a group G, is there a Banach space? Is it the isometry group of some equivalent norm on X? Okay, so this is so as it's stated, you're going to see it's wide open. Pretty good chance that it's hopeless to understand this this question. But even when X's are n, so when X is finite dimensional, then this equivalent norm business, I want to discuss the infinite dimensional will be interesting later, but even the final dimensional question is wide open. So if the dimension is finite, all the norms in Rn are equivalent. So this is really the same as asking given when is G the isometry group. Of some norm on Rn. I don't need to use the word equivalent. Right, and norms on Rn, if you want to think geometrically, right, a norm of Rn, you could just look at its unit ball, and so which is some convex origin symmetric body in Rn. Then I look when is G precisely the symmetries of a given. There exists a convex body such that its group of symmetries is G. Okay, so this is an old question. I probably it's been around forever. I've seen papers in the 70s say that Yoram Lindenstrauss asked them verbally this question, but I don't think we should give a name to this question because it's been around for a long time. I'll tell you what was known, some of what was known as we go along. So, okay, and just before I start getting into things which are more complicated, there are obvious things, obvious assumptions. It's easy to give counterexamples, right? So there obviously minus the identity. So is in the isometry group of X. So if there is a positive solution, G has to have a central involution. Okay, so maybe in most of the theorems, I would say let G be a group with a central involution. If I forget to say it, it's assumed, because otherwise the question is uninteresting. Okay, and in the finite dimensional case, G has to be compact. If I forget to say compact, I'm assuming it's compact. Otherwise, it's not interesting, etc., etc. Okay, so in infinite dimensions, it says there is some closures, properties in the weak operator topology. All these things I'll try to state, but if I forget, they're assumed. I want to make the question interesting and not trivially uninteresting. Okay. So there's a tiny subtlety, which is what do I mean by the word is? That I didn't want to get it out. It's not. I don't think it's very important. It's something that I definitely didn't notice until we wrote this paper. And definitely in the literature, people mix this up. So there are two versions of what. So you can call it the internal. Maybe first start with the external. Just mean so you're given G and you ask is G isomorphic isometry for some equivalent norm. But you could also start, that's the external version. Somehow G is given to you from outside, but you can also start with a subgroup of GLX. And then you can ask is, wow, this chalk breaks up. This is the first time I'm in a conference in 3.5 years, and I don't think I got stronger. So there's something, I mean, so this is something about the chalk here. So you're given a subgroup of invertible linear transformation, linear automorphisms of X, and you ask, is G equal to the isometry group of some equivalent norm? Okay, it's not so. Okay, this is a subtlety that should be boring, and it sounds boring, but this will be a corollary of one of the proofs I will show you today. Is that these are actually and in many papers in the literature, nobody even stated these as two different problems, or nobody said it's the same, but the people flipped from one between them. It was just, sometimes they said the word isomorphic, sometimes not. So it wasn't something that was even considered as two different questions, but this will be a corollary of what we'll do later, and I hope to show. Okay, the main steps of the proof is that these are very different questions. So for arbitrary large n, there exists let's say G1 and G2 subsets. They are subgroups of GL and R. So making that trivial, minus I is in both G1 and G2. They're compact. G1 is an isometry group of some norm under n. And G2 is not an isometry group of any norm under n. Yet G1 is isomorphic to G2. Okay, so these are different questions, and this is like a damning example. Okay, and when we'll see examples, it will follow from. So these are different questions. I'm not claiming that I think this is very important, but it's just somehow it fell out of what we did, and it's good to know that these are actually two different questions. And I think they're both equally interesting. So somehow the internal version, this is the internal version, is you're prescribing the symmetries of your convex. Suppose you're on a GL and R. You're prescribing. So I want these symmetries precisely versus the algebraic structure of the symmetries of the convex body. So any other okay. So let me just give you a few, maybe 2 or 3 known results. Some of them two of them I'll use later. So Gordon and Lowy, I think that's how, in 1979. Again, I'm breaking the chocolate. Prove that if G is finite and contains minus the identity, then G is the isometry group for some norm under n. Okay, so finite, you can always prescribe finite symmetries. Stern in the same year, prove that any group G with a central involution is the isometry group, is isomorphic. So this is the external version to the isometry group of some norm space. To the isometry group. Okay, it's going to, his construction gives an infinite dimensional norm space. And so for every G, you can construct a norm, let's say. And this is the paper that I mentioned that here they say that Jerome Lindenstrauss, who was Gordon's advisor, my advisor to ask them this question. But again, this is the first mention of that I've seen, so maybe it's due to him. I do not know. And okay, there is a long and important, and we'll get to this, and deep series of works of constructing Banach spaces with few operators. Gowers Moray, so, and we'll get to that. There is a theorem of Belenot, 1986, I think, which says that on any, and I will this theorem I will really use, and I want to say a few words about it. On any Banach space, there is an equivalent norm with isometry groups trivial. So just identity and minus identity. Okay, that's not a surprise. We can ruin all the symmetries by passing to an equivalent norm. Actually, he really needed separability. And then Yarosh, I think, proved the same thing without the word separable. Okay? And actually, that's in his paper. There's a formal statement of the, like he formulated as a question this inverse problem. So now I want to say a few words about what is the kind of thing that Belenot did, because in 5 minutes I want to use it for something. And this is something that is recurring. So if you start with your Banach space X, and you want to ruin the isometries, to make sure that there's no a trivial group of isometries, so you can start with its unit ball, take some point X outside the unit ball. Here's minus X, this is 0. Look at this line segment, and then look at the convex hull of the original unit ball with this the union of the original unit ball and the line segment between X and minus X. So he calls this a pimple. Okay, and if you choose, so if you choose wisely, so you actually use something substantial, which is you first pass to an equivalent norm which is strictly convex, even stronger than strictly convex. And if you choose wisely, you can now iterate this. Do another pimple here, etc. Okay, if you choose the sequence of points wisely, you can ensure that the pimples that you added are precisely the extreme points of this new convex of this equivalent norm. They're not too far away, so it's going to be equivalent to the original norm. But isometries preserve extreme points. So they must permute these points that you added, and then you got combinatorial information, and you can use it to show that there is no non-trivial isometry. Okay, so just the only thing I want to say is that, and that's going to be important. So this is just follows from the proof, but it's not stated, and I will need to use it. So this strategy I can make sure that the longest line segment on the boundary of this equivalent norm is as short as I want, because I can add the pimples arbitrarily close to the body. So and because I started with a strictly convex norm, then these are the only. Then I can make these additional. There are inherently to the construction. You're using extreme points, so you want to use the fact that this is not a strictly convex body. So it has line segments on the boundary, but I can make them as short as I want. Is that clear? I will need to get to that. So this is just his proof, but it's not stated. So you have to just read it. But that's what it gets. Okay. Good. Okay. So let me just give you very, very quick couple examples. Why not is not everything. So this is kind of, okay, it's obvious. So you can take, if you want, if you take G is SONR, then any norm which is invariant under SON is all going to be also invariant under all of O of N. This is an exercise. And therefore, it's going to be just a Euclidean norm. But in particular, its isometry group is O of N, not SO of N. So it's very easy to do that. I mean, right? G2, if you want, or anything, right? Acts on transitively on S6. So again, anything that acts transitively on a sphere, if it is if a norm is invariant under it, then it's invariant under all rotations. And therefore, it's the isometry group of the only norm which is invariant under that group is going to be O of N. So anything smaller than O of N, but acting transitively on a sphere is a problem for this. So there are issues that you need to overcome, and there I'll show more examples later. Analyzing these examples. Some of them are fun exercises in linear algebra that I give my students or stuff. I'll show you some more as we go along. So it's clearly not everything is going to be an isometry group of a norm. Yeah. SON minus identity. So you mean so you want if any? Okay, n is even. So for any, I should have said SON is even. Yes, it's isomorphic to the isometry group of some norm space, but not Rn. It's going to be a bigger dimensional space. Yeah, we're going to get, yeah. We'll get to that. But that follows just from Stern, for example. Yeah. Okay, so the obstruction is something completely abstract and obvious. Okay, so you can think of it has nothing to do with norms, really. So if you have two sets, A and B, and some function psi from A to B, and then F is some collection of functions from A to itself that preserve psi, right? So psi f of x is psi of x, sorry. For every x in A, whenever you have something that preserves something, okay, then something bigger also preserves it, which is what I call the piecewise closure. Piecewise closure of F. Maybe you can even think of it of F inside some bigger family of functions. It doesn't have to be a group. Functions, right, from A to itself. And it's precise. So defined. So let's go PCL, piecewise closure of F, if you want, in G, is all the functions G from A to G in this bigger class of functions. It's really abstract nonsense what I'm telling you, such that for every x in A, you can find an element F which depends on G and depends on X, but is in the smaller family, little f, such that the image of G of X is the same as the image of this F, depending on X. Whenever you have that, then also the piecewise closure, by definition, preserves phi. Because if you plug in G of X into psi, it's the same value as F, and F preserves phi. It doesn't matter that F depends on G and the point. Okay, so this is something, just a construction that you can always do. So I call it the piecewise closure. Some of my co-authors prefer to call this the vector closure in the case of groups. So that's what, so this is done. So yeah, we have different preferences for terminologies, but so in general, if you have H, let's say a subset of GLN, then instead of piecewise closure, I'll call it H hat. H hat is all the G such that this happens is the same thing. G maps every orbit to itself. Oh, really breaking the chalk here. Okay, so you start with a group, you get a bigger group. So an obvious necessary condition, so if H is an isometry group, of some norm of on our n, then H equals H hat. It has to be because that whatever that norm is, it's preserved also under H hat. Okay, so if you want to see you want the example of SON. Hat is oven, so it's indeed not the same group. And that's because if you have an element in oven, so we take G here, then X goes to G of X. It doesn't have to be in SON, but I can of course I can of course make X go to G of X just by rotating in the plane X to G of X, and that's in SON. Okay, so that's and it turns out that this is the only abstraction, and we're theorem. So H is a compact, contains the identity, then H is an isometry group of it, is the isometry group of some norm on our n, if and only if H is equal to H hat. Okay, so the matrices which are piecewise equal to elements of H, it has to force you to be in H. So I'll prove this I'll prove this later, but let me just get lots of corollaries out of this of this criterion immediately. So first, let's prove Gordon-Lewis. Right. So what happens if H is finite? Okay, then what does it mean that an element G is in H hat? Okay, this is an element, it's a matrix such that at every point, it's one of the finitely many list of matrices. Every point X, its image, its value on it is one of the finitely many matrices here. So there's a partition over N into finitely many parts corresponding to whether the elements of H are such that G is equal to those elements in one of them. But these are closed subsets. One of them has a non-empty interior. Linear, or it has to contain just a basis. Okay, so it has to be. So this just finishes Gordon-Lowy. And our proof is very, very inspired by the way they proved it. Okay, so what other thing? Oh yeah, maybe this example is a good one. It also explains what's happening with H hat. So if you start with this H, compact, and as I said, minus identities in H, then let's think of it as a group acting on Rn to the n. So H acts on Rn to the n, which is Rn squared. What? No? So by diagonally, right? So you can take an element H in H and assign to it the block matrix H. So okay, so when you think of H as a subgroup of matrices n squared by n squared matrices using the block diagonal, then the hat equals itself. Let's just do this exercise to get used to it, to see what's happening. So so if you think of H as a subgroup, so if I think of call this subgroup this called then I claim easy exercise that G hat equals G. And why is that? So let's just check. So take an element G in G hat. Okay, and you can write it in block form. So G is G11, G12, etc. Okay. But what happens when you apply G to a vector V000? Then right, you're supposed to get G11V, G12V, etc. But it's also equal to some element of H, which is a block diagonal. So it's also equal to some H, G, V. It's not V in 1 because I put the first and then 0. But this in particular shows that this is true for every V, that all of these, the off-diagonal terms are the 0 matrix. Okay, so actually what you see here is just a block diagonal matrix. So G is really G1, G2, Gn. But these are all equal to each other because I can now apply G to the vector V in all the coordinates. So this means that, and this is also one of the elements in H. So actually G1 equals Gn. But then I can also apply it to any basis, E1 up to En. And this is again an element of H, depending on this vector. But now G, this is the values of G on a basis. So G is simply, I just, by adding this block diagonal, I forced G to be actually of this form, HHA. Is that clear? I did it. This is just an exercise that you can give to students. Okay, so what you get from this is that right? What was this G? G was just you can, if H is a subgroup of GL and R, which with the what we need H compact and minus identities in H, then we saw that if we think of H tensor the identity as an element of GL Rn tensor Rn, that's the same thing as what we just wrote. If you tensorize with the identity, this is an isometry group. Of some norm. On Rn squared. So you can call this is a solution of the stable version. Like if you tensorize with the identity, then everything is an isometry group, and that answers your question. So if you do that to SON, it will be an isometry group of something, but of a bigger dimensional space. You just tensorize with the identity. But you see exactly what was the role of the hat. We needed this additional information so we can apply it to a basis that will force H to be inside. Okay, so I think it explains what's happening here. But as a corollary, you get that in particular, so any compact Lie group with the central involution is an isometry group. Of a norm on Rn for some n equals n of G, n of, I should give it a name, any compact Lie group G. Okay, and this is just because you just need any faithful representation for which this involution goes to minus the identity. That's you can deduce this easily from Peter Weil, and then just you get that faithful representation, then tensorize it with the identity, with the block form, and you get it. Okay, so you get any Lie group on some dimension, but I don't know what the minimal dimension is. There are things to there are things to ask that I didn't think about. I want to prove the main theorem because there is something fun there, but I want to show another, I think, probably more major corollary of it. Definitely, it's a very deep theorem, what I'm going to show you now because of what it uses. So, so this external problem, I give you a Banach space and I ask you, characterize which groups are the isometry group, are isomorphic to the isometry group of some equivalent norm on X. So there is no, except there was no space for which the answer was known. We don't know the answer for Rn, we don't know the answer for L2, for LP spaces. All of these, I think, are very challenging questions. Okay, but we can construct one infinite dimensional Banach space for which we can solve the problem. So this is a theorem, if you want. There is a Banach space X such that group G is isomorphic to the isometry group of some equivalent norm of X, if and only if G is isomorphic to H times -1, where H is a compact Lie group. Lie group with a central involution. Okay, so so this is just so this solves the isomorphic problem for this space X, and this is the only space. Prior to our work, no space solution was known for. This is the only space which we currently know how to solve this inverse problem for. So in like funny things, so in particular, you get that right, Z mod 4 Z is not the isometry group because it doesn't split like that. But yeah, Z mod 2 times Z mod 2 is, and in particular, there were going to be two distinct central involutions, not only just one, because there is one in here, and then so all kinds of things like that come from this. But this is okay. So let me tell you why this is so. How we can use this stable version of the yes. Really? So okay. So I felt that it's a double failure, right? I'm fixing the clock and fitting the material that I planned. Okay, so it's 5:15. Okay, let me show the proof of this corollary, and then I'll I'll quickly explain how to prove the theorem, and then show there's a lot more that we know. Okay, let me at least finish what I started here. Okay, then. And I'm not going anywhere, so if anybody wants to hear more, I'll be happy to tell you. Okay, so let's prove this corollary. It's using the stable version of the problem. Okay, so the main input is a very nice paper of Rosendahl, sorry, Ferenczi and Rosendahl. Which shows that there exists a space X such that any isometry group, so it's really just essentially one of these directions, any isometry group of an equivalent norm on X has the following, induces a, so induce, if H is a subgroup of GLX containing the minus identity, and it's the isometry group of some equivalent norm on X, then you can decompose X as Y direct sum with Z, where this direct sum respects the action of the group. Y is finite dimensional, and H, X, and Z is plus minus the identity. So they call this nearly finite dimensional. There's some term that they gave. So any subgroup of GLX, if it's the isometry group of some norm, then X splits into something finite dimensional, and the rest is H is acting trivially on it, plus minus the identity. So because H is the isometry group essentially of something finite dimensional, then it's a Lie group. I should have called it G, right? The part that's acting on Y is going to be a Lie group, and here's the plus minus ones, and you get that direction. This is the fact that such a space exists is a big deal. Okay, so it's this is the Gowers-Moray construction, but it doesn't work as is. You need to enhance it by some very nice work of Ferenczi, and even Ferenczi's work doesn't work. That doesn't finish it, and there is an old theorem of Shankovsky that finds an appropriate subspace of Ferenczi space, and this space, just writing it down is a big deal. The fact that this exists, and it solves many other big open questions. So this is deep, not because of anything I did, but just because it's quoting a lot. Okay, this is a very deep result that you can have such a thing. But now let's go to the reverse. So this is where we come in. We want to show that whenever G has this form, I can cook up an equivalent norm on X, which says that this is exactly its isometry group. Let's do that. okay, so what is the setting? So we have H is a compact Lie group with central involution. And so by the theorem that I erased, the stable version of this isometry problem, we know that H is isomorphic to the isometry group of some norm let's call it on Rn for some n, right? Okay, that's what we just did with this. Okay, now this finite dimension. So in any Banach space, I know there is this Kaditz-Snowbar theorem. Okay, in any case, you don't need that in this case. Any finite dimensional subspace of a Banach space is complemented. There is a bounded projection onto it. In this particular case, I can ensure that the norm of the projection is even 1 plus epsilon, but I can write the x of this that they got of Ferenczi and Rosendahl. I can write it as Rn, the reg sum with y, and by that I mean equivalent norms. I didn't tell you what the norm. I can come up with a norm space y such as x is such that x is isomorphic to Rn direct sum with y. And I just take any n vectors like with their span, it's a complemented subspace. So there is Rn and there is the complement, which is okay. But what we're going to do now is we're going to put Belenot's norm on y. Okay, so let norm beta, let's say for Belenot, be an equivalent norm on y, an equivalent norm such that the isometry group of is just minus identity, and I will need that the longest line and the longest line segment on the boundary of the unit ball of this norm is less than a half, maybe only a quarter. I don't know. But I can make it as short as I want because of this pimple construction. Okay. So now when define the norm, so I think of define a norm. So if you have x, y in Rn, the x sum with y, I'll just define the norm of x, y to be the H norm that we got of x plus the Belenot norm of y. And now the real fun comes. We're trying to show that there is no new isometries that you generated. Clearly, H times minus 1, 1 is in here because H x is isometric on the first coordinate and plus minus 1 here. I want to show that nothing else exists. So let's show that. So the claim is that any G in this isometry group is of the form G xy is H x plus minus 1. Okay, when H is in the group that I started out with. Okay, so what we know is that we can write G of xy is what ax plus by cx plus dy, where a is from Rn to Rn, b is from y to Rn, C is from Rn to Y, and D is from Y to itself. So I'm just saying that G is A, B, C, D in block form. Okay. So let's first show that C is 0. So suppose that C is not 0. I'll get a contradiction. I think C, let me make sure what I want to start with C. Yeah. Yeah. So first of all, so there is some there is some X in Rn such that C of X, the C of X, the Belleno norm of it is 1. So okay, so let's normalize it, and now take K in the kernel of B such that the H norm is 1. So the kernel is non-trivial just because B is mapping an infinite dimensional space into Rn. Okay, so to take any okay, so and then so what does this mean? It means that so now let's look at this computation. So look at G of, so the norm of Ky, which is 1 plus the norm of Y, right? The norm of K plus the norm of beta 1, norm of Y, is also equal to the norm of G, Ky, which is the AX plus BY in the H norm plus the CX plus DY in the beta norm, the Belleno norm, and it's less or equal than AX plus BY, just doing the triangle inequality, plus CX plus DY, right? And which is, so this plus this is just the norm of X0, of G of X0, and the other one is the norm of G of 0Y, and not X is K, right? Okay. Okay, which is 1 plus Y, right? This is the norm of G. G is an isometry. Okay, so 1 plus the norm of Y. So there's equality throughout. Oof. Whoa, yeah, I'm holding my notes and not looking at them. There's an X, right? I'm sure I'm taking. Okay, sorry. That was XK. I mean, it was just a prop, I guess. X. So very sorry. So this is XH plus 1. Because, yes. And then XK, AX, sorry about that, BK Cx plus dk ax bk cx dk. And then what? Ax. So indeed, this is x0, 0k, and there's equality throughout. Okay? So therefore, we have that in particular, one of these triangle inequalities. So Cx plus dk in beta has to be equal to the norm of Cx beta plus dk beta. B was in the where's the y? What do you, I don't even see a y on the board anymore. Thanks. Okay. Sorry. Okay. So and now yeah so this is a unit vector. I should have said that dk, right? What is the where was k? K was in the kernel. So the norm of 0k is 1. That's a, but it's also, because it's in the kernel, it's so bk 0. So this is the same as the norm of dk. So dk is 1, right? Just I'm using the fact that k is in, this is where I use the k is in the kernel. So these are both unit vectors, and there is equality in the triangle inequality, and therefore this gives us an interval of length 1 on the boundary of the unit ball, so, and which doesn't exist. Okay, so that is so I found these kinds of arguments. People in the theory of isometries and Banach spaces have usually the people have been interested in isometries in L1 sums of strictly convex Banach spaces. So some of this was hidden in many places, but here it's not strictly convex. But you have a bound the length of the intervals in the boundary. Okay, so this killed C. And then let me not make typos again. And then so now I want to show that B, so take any y, for every y in y, look at what G does to the vector minus A inverse by y. Okay, and so you get minus A inverse by. Is going in the, correct me that I didn't make typo. This is correct. These are in the right spaces. This is in the H norm, and this is in the H norm, in the beta norm. Okay, and then if you write this out and you do the same triangle inequality, you get again equality in the triangle inequality for the same reason, and you get that that there is that minus A inverse by. If you apply A to this and B to that, there is equality in the triangle inequality here. So this is the same as minus A inverse. Oh, sorry, I should have said before that just the mere fact that that C vanishes means that A is invertible. I should have said that, because that's where I'm using this is Rn, because the norm of x0 is the norm of x. H is a norm on Rn, but this is also the norm of Ax plus C, which is 0, C X, right? Because that's what A does, but this vanishes. Okay, so A is actually an isometry, and this is finite dimensional, so it's invertible. So I can look at this element. And then when you apply the formula here to that and do the same triangle inequality, you just get that there's equality in this triangle inequality. This is H plus by H, which is, of course, this is 0. And this is twice by. And this H. So this was for every y, so b is 0. So actually the isometry is block diagonal, but and therefore each of A and D are isometries, and we know D is minus plus minus identity, and A belongs to H. Okay, so that solves, this is the only space for which we know how to answer the question. I have no clue what the time is. I'm probably over time. I can't see that. Okay. Okay. So so this criterion, right? So I want to say that H hat equals H, remember, was the only obstruction for being the isometry group of some norm on our N. But I do not know. It's a nice question. What happens in infinite dimensions? Because the proof will use algebraic geometry, which I just basic facts, but I only know in finite dimensions. Okay. So we're just again mimicking this what Bellano does and all of that. We're going to encode everything in a nice set of extreme points. So the proposition is that so we have H inside ONR. But I should have said, but the fact that H is compact, there is some invariant scalar product on our end, so we can always assume that the standard scalar product is invariant under H, and then there exists some finite subset phi of the sphere such that H hat is all the G such that G H phi is H that preserves just the orbit of the set. Okay, so this uses the fact that any compact that it's an algebraic set and the Noetherian property in some way. I won't have time. I wanted to show the proof. It's a fun proof that but the minute you have this finite property, then you will just consider the convex hull of this finitely many union of orbits, and because these are points on this okay, so yeah, I forgot something. So, and I'll need this later. I don't have much time, but if you fix a finite subset, so for every finite subset, we can ensure that phi contains this given finite subset. Okay, that's a so if we start if phi contains, let's say, the standard basis and also EI plus EJ over root 2. Okay, then anything which is which maps these sets to the sphere must be an orthogonal transformation. Just write it out. Okay, so its forces being an orthogonal transformation. So if G is in H hat, then in particular it's in oven. A priori it's not obvious, but if it just maps all of H phi to itself, which is a subset of the sphere, H with a subset of with a subgroup of oven. It maps all of this to a subset of the sphere, in particular these points to a subset of the sphere. Therefore, G is in oven. So right? So if G is in H hat, then G is in O(n). And if it is isomer, if it preserves, so first of all, this is, sorry, I didn't, so here I don't need that the minus identity belongs to H, but in the theorem, minus identity does belong to H. So this is an asymmetric convex set. So it equals to minus itself. So this is a unit ball of some norm. If G preserves this norm, it preserves the extreme points. But these are precisely the extreme points because this is a subset of the sphere. So there works, and it's a convex hull of this polytope or whatever that is. Okay, so you just have to prove this finite determination property, and that uses a little bit of algebraic geometry, and so it's a random construction. One thing that when Emmanuel Boyard gave a talk about this is like the baby version of the theorem. I think Martin Breidson asked him, okay, you're using these extreme points, can you make the norm smooth or uniformly convex, etc.? Because we're really using like that, we're encoding the combinatorics of the extreme points, and we can. So we can also make this norm in the theorem, which is that if H equals H hat, then it's the isometry group of a very nice norm. It has moduli of uniform continuity and smoothness as close as you want to that of Hilbert space. But that requires more work, and I plan to show it. So even though we're using this combinatorics of tracking where extreme points go, we can also make the body very nice and smooth. Okay, that was just hand waving. This is just the beginning. So Pandora's box has been opened because now you can ask yourself, what are the subgroups, the compact subgroups of GLN of R, which this is now has nothing to do with geometry. This is a very nice algebraic question, which I'm very shocked if anybody, I mean, I talked with many group theorists that this question, when is a group equals to its piecewise closure, was not studied in group theory. So this is now a purely group theoretical question. And we have, so there is a lot of, we saw the issue of transitive actions and spheres coming up, and these have been classified by Armand Borel and Samuelson and Montgomery and Samuelson. And then there are other obstructions to these three homogeneous spaces, which also have been characterized. There's a lot of very serious work behind this, and using all of this machinery and examining the tables, we can prove a lot of theorems. So there is a lot of now group theory going in here. And so we just, yeah, so I showed you 10% of what we know. Let me, like, one of the corollaries of what we know is that so if H is not equal H hat, so okay, and another thing that I didn't get to is that it's enough to deal with connected groups. So if you have a group is the isometry group of some norm, if and only if the connected component of the identity is the isometry group of the norm. That requires proof. So we can reduce the question to isometry groups, to connected groups, and for connected groups, if we know if you have, so again, so if let's say if H X irreducibly, if so H is compact, connected, a subgroup of GLN R, minus identities in H. So if H hat 0, the connected component is not H is connected itself. If this is not happening, then there is a finite list, explicit list of exceptions, some infinite families and some exceptional groups, etc., that we understand. And what remains, then, except for a finitely, I'm not saying it, I'm not trying it, except for a finitely concrete list of exceptions, we can write, there's a table in the paper. What you get is that n has to be even. So Rn is, you think of it as C to the m. And H hat, connected component, is T1 times H. So right, a multiplication by complex numbers. So that's the only possibility. So in particular, any norm which preserves which H preserves, a priori it was over R, but it's actually a complex norm. Okay, and so there are all kinds of theorems of this type, and you can get that the normalizer of any such group is always the isometry group of a norm, and there is a whole lot of things that we know how to say, but we do not know how to answer the question. And the big abstraction, the big open question that remains, if you want to understand, to characterize isometry groups of norms, is actually what happens. So we somehow understand the local issue. We understand when H is the connected component of the identity of H hat, unless and somehow the dimension of H hat increases. There's a T1 times H. Okay, but what happens when they're both when H is just finite index in H hat? This is exactly what we saw with SON of R and O of N of R. Okay, so this is not a local issue. Somehow, when you look at, I want an intrinsic characterization of those H for which H hat equals H. So in the connected world, we do have a characterization. It's ugly, it has tables, etc. But we have a characterization. And we do not know how to understand what happens when somehow being for a norm, like in SON, a norm being invariant under SON means that you're also invariant under O of N, but that's somehow far away. That's a completely different connected component. So we do not understand how to rule out or what kind of finite index situations we have. So somehow we solve the virtual version of the problem, and we still don't understand how new connected components can come up. And I think that's the big thing that remains in the finite dimensional setting. And in the infinite dimensional setting, how do we solve the problem for Hilbert space? LP spaces. We just have this crazy space for which we did this construction, but there's only one example for which we know the answer. So yeah, I'll stop here. I have no idea how much time but it's my fault. But
are there questions for Assaf?
So this is more a curiosity, because I guess it goes somehow in the direction opposite to your talk. I guess that one would expect that if a space admits an Hilbert norm, so if it's an Hilbert, well, that is the most symmetric one, right? With the largest.
You're talking infinite in Rn, of course.
Infinite dimensional,
yes.
let's say. Well,
yeah,
okay.
Yeah, I agree. Yeah.
Okay, so, but can this be stated in a way saying that it's the space with the largest, I mean, the Hilbert norm is the one with the largest, whatever that
So
means.
there is this, it's very old. I never thought about it, but there's surveys, there's this Mazur rotation problem, which if you Google it, it's a famous problem. There are surveys about it, which is, it's conjectured that the only Banach space for which the isometry group X transitively on its sphere is a Hilbert space. Okay, but that's open. So that's a very, very, very old question. I never thought about it, but I think it's a big deal to solve it. So you're asking a question. It's the Mazur rotation problem. It's a famous question.
Other questions? All right. I propose we kill two birds with one stone and thank both the SOF and the organizers again.